Go on, take a moment. Feel that? The feeling of being perfectly still. The solid floor beneath your feet. You are, for all intents and purposes, motionless. But that feeling, as real as it seems, is maybe the biggest illusion there is. It's a comforting lie your brain tells you every second of every day to hide the fact that you're on a cosmic joyride of unimaginable speed. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. You are not still. Not even a little bit. You're a passenger on a spinning, tumbling, racing spaceship called Earth, hurtling through the void on a journey so massive it's hard to wrap your head around. The ground you think is so solid is actually a platform whipping you through space at thousands of miles per hour, which is riding a bigger platform moving hundreds of thousands of miles per hour, which is part of an even grander structure falling through the cosmos at over 1,000,000 miles per hour. So if everything, and I mean everything, is in constant, frantic motion, what does it even mean to be still? If the whole universe is expanding, like a balloon inflating in every direction, what are we standing still relative to? That's the question we're here to answer. We're going to peel back every single layer of your motion, from the spin of our own planet to the very edge of the observable universe. And by the end, we'll uncover the beautiful, paradoxical truth of what it really means to be motionless. This trip is going to change how you see your place in the universe forever. The everyday illusion. Before we get into the cosmic stuff, let's start with an illusion that's a little closer to home. Picture yourself on a brand new, high-speed train. The ride is impossibly smooth. You're just sitting there, maybe scrolling on your phone. You take a ball out of your pocket and toss it straight up. Where does it go? It goes up, and it comes straight back down into your hand. It doesn't fly to the back of the car. As far as you and that ball are concerned, you might as well be in your living room. Now, you take a sip of coffee. You don't have to brace yourself. Inside that train car, the laws of physics feel totally normal, totally stationary. But then, you look out the window, and the world outside is a blur. Trees and stations are whipping past at 100 miles per hour. To anyone standing on the platform, you are the blur. You, your coffee, and your ball are all screaming through the landscape. So, who's right? Are you still, or are you moving at 100 miles per hour? The answer, and this is the first key to everything, is you're both. It all depends on your frame of reference. A frame of reference is just the background you use to measure motion. Inside the train, your brain automatically picks the train car as its reference frame. Why? Because everything inside the floor, the seats, the air, you is all moving together as one unit. Since nothing is jostling you relative to the walls of the train, your brain logically concludes you're at rest. The second you step off that train onto the platform, your reference frame instantly switches. Now, the platform is your still point. And that same train you were just in is suddenly a massive metal bullet rocketing down the tracks. You switched your frame, and you switched what's still and what's moving. Think about cars on a highway. You're going 60. The car in the lane next to you is also going 60. You can look over and make eye contact with the driver. Relative to each other, you're barely moving. But then a car passes you going the other way, also at 60. To you, your combined speed is a terrifying 120 miles per hour blur. There's no single, absolute speed. There's only speed relative to what? This idea is called the relativity of motion. We feel stationary because we're inside a local bubble, a room, a car, a train that moves as a single chunk. As long as there are no sudden starts, stops, or turns, our brain just defaults to this local bubble as the definition of still. But our local bubble, our planetary train car, is moving way, way faster than you can imagine. It's time to zoom out. Layer 1. The planetary spin cycle. Alright, let's leave the train and stand in an open field. Nothing but solid earth and open sky. Here, you've got to be still. Right? Nope. Right now, you're standing on the surface of a giant, spinning ball. That ball, planet Earth, is rotating on its axis. And depending on where you are, your speed is wild. If you're at the equator, you and everything around you are being flung eastward at about 1,040 miles per hour, or 1,670 kilometers per hour. That's faster than the speed of sound. So why can't we feel it? Why aren't we all holding on for dear life? It's the same reason as the train. Everything is moving together. The ground, the oceans, the buildings, and most importantly, the thick blanket of atmosphere are all spinning in almost perfect unison. This is our planet-sized reference frame. When you drop a ball, it falls straight down because you, the ball, and the ground were all already moving eastward at that same incredible speed. But unlike a windowless train, our planet has windows to the outside. The most obvious effect of the spin is day and night. The sun doesn't rise and set. The Earth is spinning, carrying you into the sun's light and then back out into its shadow. Every sunrise is proof that you're on a rotating platform. There are subtler clues, too, like the Coriolis effect. This is what makes moving things like air currents, ocean currents, and even long-range missiles appear to curve. It's because the ground beneath them is rotating at different speeds. At the equator, the speed is fastest. At the poles, your speed is basically zero, you just do a slow pirouette once a day. This difference in speed is what gives hurricanes their spin and drives global weather patterns. So, this first layer of motion is huge. You're on a carousel spinning at supersonic speeds. But this dizzying spin is just a tiny wobble on a much grander journey. Let's zoom out again. Layer 2, the annual solar race. That spinning ball you're on isn't just spinning in place. It's on a long, gravitational leash held by the sun. As the Earth spins, it's also hurtling through space in a giant, nearly circular path around our star. This is its orbit. And the speed is almost unbelievable. Right now, you are traveling around the sun at an average speed of 67,000 miles per hour. That's about 107,000 kilometers per hour, or 30 kilometers every single second. In the time it took you to read that last sentence, you traveled nearly 200 miles through space. Think about that. 67,000 miles per hour. And you feel nothing. No cosmic wind in your face. Why? The answer is a beautiful concept: freefall. The Earth is in a constant state of falling toward the sun. Gravity is always pulling us straight in. But at the same time, the Earth has a massive amount of sideways momentum left over from its formation, a tendency to fly off in a straight line. These two forces are in a near-perfect balance. The sun's gravity just keeps bending our straight-line path into a stable orbit. It's like a group of skydivers. As they fall, they can look at each other and feel like they're just floating. Relative to one another, they're motionless. But relative to the ground, they're plummeting at 120 miles per hour. We are all skydivers on spaceship Earth, falling in a graceful arc around the sun. And because the planet and everything on it is falling at the exact same rate, we don't feel a thing. It's our new, stable reference frame. And just like with rotation, the evidence is all around us. The most obvious is the year. That 365-day cycle is just the time it takes us to do one full lap on our cosmic racetrack. The changing seasons are also a direct result of this journey, caused by our planet's axial tilt. And here's an ancient clue: the night sky. As the Earth moves from one side of its orbit to the other, our view of the universe changes. The constellations you see in winter are different from the ones you see in summer because you're looking out in a completely different direction into space. The 12 constellations of the zodiac are basically just the celestial wallpaper that lines our annual path. So our motion is getting more complex. We're on a planet spinning at 1,000 miles per hour, while that whole planet is orbiting the Sun at 67,000 miles per hour. Surely that's the end of it. The Sun, that giant anchor of our solar system, must be the final, stationary point, right? Oh, not even close. We're just getting started. Layer 3. The galactic neighborhood. That enormous star you're orbiting, the Sun, is itself just a tiny speck on a far grander journey. The Sun is just one of hundreds of billions of stars that make up our home galaxy, the Milky Way. And just like the Earth orbits the Sun, our entire solar system is orbiting the supermassive black hole at the center of our galaxy. This journey dwarfs everything we've talked about. Our solar system is moving through the Milky Way at an average speed of around 514,000 miles per hour. That's about 828,000 kilometers per hour. At this speed, you could fly around the entire Earth in less than 3 minutes. Our true path through the galaxy isn't a simple circle, but a gigantic, sweeping corkscrew, a helix. We are spiraling through the cosmos, tethered to a star that's on its own grand journey. And again, we don't feel this 500,000 mile per hour velocity because our entire solar system, the Sun, the planets, everything is moving together as one gravitationally bound family. Our reference frame has just expanded again. We're still, relative to the Sun, which is itself moving at this incredible speed relative to the galaxy's center. The scale of this orbit is staggering. It takes our solar system about 230 million years to complete a single lap around the Milky Way. This is one galactic year. To put that in perspective, the last time our solar system was in this same spot, the very first dinosaurs were just starting to evolve. When T-Rex was alive, we were on the complete opposite side of the galaxy. The entire history of humankind has taken place in a tiny fraction of a single galactic orbit. So, we're on a spinning planet, orbiting a star, which is spiraling through a galaxy. We've peeled back 3 layers of motion. But our entire galaxy, this magnificent spiral of suns, is also on the move. Okay, let's take a breath. We've gone from a quiet room to a 500,000 mile per hour spiral through the galaxy. If your sense of stillness is starting to feel like a distant memory, and your mind is spinning as fast as the Earth, then hit that subscribe button. Because we are about to take an even bigger leap into the motion of galaxies and the fabric of spacetime itself. Also, we'd love to know, which layer of motion has blown your mind the most so far? Let us know in the comments. Layer 4. The Great Cosmic Dance. You might think that this is the end of the line. But the universe is never that simple. Our entire Milky Way galaxy is caught in a cosmic dance with its neighbors. First, there's the Andromeda Galaxy, our closest major galactic neighbor. Andromeda is heading right for us. Or, more accurately, we're heading for each other. Pulled together by gravity, we're converging at about 250,000 miles per hour. But don't panic. In about 4.5 billion years, our 2 galaxies will start a long, slow process of merging, passing through each other like ghosts since the stars are so far apart. Eventually, we'll form one giant, new galaxy. But even that is just a local event. The Milky Way is part of a small group of galaxies called the local group. The local group is on the edge of a much larger structure called the Virgo supercluster. And this entire supercluster, thousands of galaxies, is being pulled towards something else. Back in the 70s and 80s, astronomers noticed that our whole patch of the universe seemed to have an extra, unexplained motion. A large-scale drift. They were being pulled by a huge, unseen concentration of mass they nicknamed the Great Attractor. Today, we know the Great Attractor is the gravitational center of an even vaster structure called the Laniakea supercluster. Laniakea, meaning immeasurable heaven, in Hawaiian, is our home supercluster, a sprawling network of roughly 100,000 galaxies stretching over 520 million light-years across. And we, along with our entire local group, are falling towards its center. This motion is the fastest yet. Our galaxy, the Milky Way, is being dragged through intergalactic space at a staggering 1.3 million miles per hour. That's 600 kilometers every single second. This is the sum of all the gravitational tugs from nearby galaxy clusters and the massive pull of Laniakea's core. The how do we know? Interlude. Okay, pause. 1.3 million miles per hour. These numbers sound like fantasy. How could we possibly know this? We know these speeds with amazing confidence, not by looking, but by listening to the oldest light in the universe. The first clue is the Doppler effect. You know it from ambulances. The siren pitch is higher as it comes toward you and lower as it goes away. The same thing happens with light. Light from an object moving toward us is compressed, shifting it toward the blue end of the spectrum, a blue shift. Light from an object moving away is stretched, shifting it to the red end, a red shift. By measuring the exact color shift from distant galaxies, astronomers can calculate their speed relative to us with incredible accuracy. But relative to what? This is where the most important piece of evidence comes in. The cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang itself. It's a faint hum of microwave radiation that fills all of space, released when the universe was just 380,000 years old. Because this radiation fills the entire cosmos, it acts as the ultimate practical reference frame. It's the closest thing to a universal, at rest, background we have. If we were truly at rest in the universe, we'd see the CMB as having the exact same temperature in every direction. But that's not what we see. We see that the CMB is slightly warmer, and therefore blue-shifted, in one direction, and slightly cooler, and therefore red-shifted, in the exact opposite direction. This pattern is our motion sickness footprint on the cosmos. It's the definitive proof of our motion relative to the rest frame of the early universe. By measuring the size of this temperature difference, we can calculate our speed. And the number it gives us is that astonishing 1.3 million miles per hour. The final twist. Space itself is expanding. So we've measured our motion relative to the oldest light in the universe. We have a complete picture of our velocity. But here, at the very end, comes the most profound twist of all. The very stage on which all of this is happening is itself expanding. This is fundamentally different from everything else we've discussed. The Earth orbiting the Sun is an object moving through space. The expansion of the universe is the fabric of space itself stretching. The classic analogy is a loaf of raisin bread rising in an oven. The raisins are galaxies, and the dough is space. As the dough expands, every raisin moves away from every other raisin. A raisin isn't moving through the dough. The dough is carrying it along. From any one raisin's perspective, it looks like all the other raisins are rushing away from it. This is exactly what astronomer Edwin Hubble discovered. He observed that almost every distant galaxy showed a redshift. They were all moving away from us. And he found a clear rule, now known as Hubble's law. The farther away a galaxy is, the faster it appears to be moving away. This was the first proof that the universe is expanding, and it shatters any idea of a fixed, absolute reference point. Because if space itself is being created between galaxies, there's no fixed grid to be still against. Every point is the center of its own observable universe. An observer in a galaxy a billion light-years away would see us rushing away from them, just as we see them rushing away from us. For distant galaxies, the amount of space expanding between us is so vast they can recede from us faster than the speed of light. This doesn't break relativity, because it's not an object moving through space. It's the space between us that's stretching. Now, figuring out the exact speed of this expansion, the Hubble constant, is one of the biggest challenges in cosmology today. Measurements of the early universe suggest one speed, while measurements of the modern universe suggest another, slightly faster one. It's a fascinating mystery called the Hubble tension, and scientists are working hard to figure out what it means. What it means to be still. So, after this wild ride, what's the final answer? If everything is expanding, what are we standing still relative to? The simple answer is, you're standing still relative to your immediate reference frame. The floor, the air, the planet. That feeling of stillness is a real, physical experience of being in balance with your local environment. But that's just one tiny piece of the story. Because that local bubble is on an incredible journey. You're on a planet spinning at 1,000 miles per hour, which is orbiting a star at 67,000 miles per hour, which is spiraling through a galaxy at over 500,000 miles per hour, which is falling toward the Great Attractor at 1.3 million miles per hour. And the fabric of space itself is expanding underneath it all. On a cosmic scale, there is no such thing as still. There's no ultimate anchor. Stillness is a purely local and relative concept. It's a story told from your point of view. Change your reference frame, and you change the story. So the next time you're sitting in a quiet room, feeling that perfect stillness, smile. Acknowledge the illusion, but also cherish the reality of it. You aren't just motionless. You are a quiet observer at the heart of a cosmic explosion. You are the still point in your own story, a temporary anchor in the chaos, surfing an unimaginable wave of expanding spacetime. That feeling of stillness is your ticket to the show. It's the reference point from which you get to witness the entire, glorious universe in motion. The universe has no edge, and it's freaking me out. We learn it from the time we're kids. Everything has a beginning and an end, a center and an edge. Your house has walls. Your city has limits. Even our planet has a boundary, that precious, thin layer of atmosphere separating us from the cold, silent void. Everything we know, everything we can touch and measure, is contained. It has a shape. It has an outside. This idea is so hardwired into our thinking, it feels like a basic law of reality. It's our brain's operating system for making sense of the world. A container holds things. A road starts somewhere and ends somewhere else. A story has a first page and a last. But what if the single biggest thing we know, the entire universe, all of space and time, breaks that rule? What if the cosmos has no edge, no outside, for it to expand into? This isn't just a philosophical brain teaser. It's what cosmology tells us is probably true. And this idea might just break your brain. Frankly, it's freaking me out. It goes against the most fundamental assumption we have about existence. So, let's get freaked out together. Let's take a trip to the very limits of our intuition and see if we can wrap our heads around a universe that is truly, deeply, and beautifully boundless. The intuition problem. Let's really get into why this idea is so unsettling. Our entire evolution, biological and psychological, happened inside a world of boundaries. For our earliest ancestors, knowing the edge of the forest, the border of a rival tribe's territory, or the shoreline was a matter of life and death. Edges define safety, resources, and who we are. This is more than just a habit. It's a cognitive framework. Psychologists talk about Container schemas, mental structures we form as infants. We are in a room. We put food in our mouths. We take a toy out of a box. In and out, containment, boundaries. These are the first spatial relationships we ever learn. They are the absolute building blocks for how we reason about the world. So when a cosmologist casually says, the universe has no edge, our brain basically files a bug report. It's a syntax error. It's like being told to imagine a color that's not on the spectrum. The question that immediately pops into our heads is, okay, but if it's expanding, what is it expanding into? That question feels so logical, so necessary. In our world, for something to expand, it has to push against something else. A balloon inflates by pushing the air in the room out of the way. A city grows by paving over fields. The very word, expansion, implies a frontier pushing into new territory. So, when we hear the universe is expanding, we instinctively picture a bubble. Inside is all the stuff: galaxies, stars, us. Outside is what? An infinite black void? Nothingness? And we see our universe as this growing sphere of something, pushing into that endless nothing. But here's the first major mind bend. That picture is completely wrong. To understand why, we have to perform a kind of mental surgery on our intuition. We need to retrace the steps of one of the greatest intellectual revolutions in human history, which shattered our cozy view of the cosmos, piece by piece. A journey through a smaller cosmos. For most of human history, the universe had very clear edges. It was cozy, it was understandable, and it was centered, reassuringly, on us. To ancient Egyptians and Babylonians, the world was a flat disk floating in an ocean, with the dome of the sky a solid bowl holding the stars right on top. It was a snow globe, and we were the main attraction. It had an edge. You could, in theory, sail to it. Even the ancient Greeks, who brilliantly figured out the Earth was a sphere, still put it at the center of a finite cosmos. The Ptolemaic model, which dominated Western thought for over 500 years, was a set of nested Russian dolls. Earth was motionless at the heart. Around it were crystal spheres carrying the moon, the sun, the planets, and finally, the outermost sphere of fixed stars. This was the final boundary. Beyond it lay the realm of the divine. The universe had a clear, defined, and sacred edge. It was a comforting picture. It gave us a specific place in an ordered reality. The universe was made for us. But then, cracks started to appear in that perfect celestial sphere. The Copernican revolution was the first earthquake. Nicolaus Copernicus suggested the sun was the center, and Earth was just another planet. Suddenly, we were demoted. This was deeply unsettling, but even early heliocentric models often kept the outer sphere of stars. The universe got bigger, but it was still a contained, knowable place. But thinkers like Giordano Bruno took it a step further. If the Earth is just a planet orbiting a star, what about all the other stars? Weren't they just other suns, incredibly far away? And didn't they have their own planets? Bruno imagined an infinite universe with countless worlds, no center, and no edge. For this and other heresies, he was burned at the stake, a testament to how terrifying this idea was. Even Isaac Newton, whose laws of gravity govern the cosmos, wrestled with this. His own laws implied an infinite universe. In a finite universe, gravity should pull everything into one giant clump. The only way he saw for the universe to be stable was if it were infinite, with the gravitational pull on any star being roughly equal from all sides. But an infinite, static universe had its own problem. In the 19th century, astronomer Heinrich Olbers asked a simple but devastating question. If the universe is infinite and full of stars, why is the night sky dark? In that kind of universe, your line of sight should land on the surface of a star no matter where you look. The entire sky should be as bright as the sun. This puzzle, Olber's paradox, was a huge clue that something was profoundly wrong with our picture of the cosmos. The answer wouldn't come from pure thought, but from a new generation of giant telescopes. The Great Rupture. Hubble's discovery. The story of our modern, edgeless universe really begins in the 1920s at the Mount Wilson Observatory in California. There, an astronomer named Edwin Hubble was using the most powerful telescope in the world to settle a debate. Were the faint, fuzzy patches called spiral nebulae gas clouds in our own Milky Way, or were they entire, island universes far beyond it? Hubble focused on the Andromeda Nebula. By finding special stars called Cepheid variables, which pulse at a rate tied to their true brightness, he could calculate its distance. The math was undeniable. Andromeda wasn't in our backyard. It was a colossal galaxy, just like ours, almost 1 million light-years away. We now know it's closer to 2.5 million. In that moment, the known universe exploded. The Milky Way wasn't everything. It was just one galaxy among countless others. As staggering as that was, what Hubble discovered next tore up the rulebook forever. Working with his colleague Milton Humason, Hubble began measuring the light from these new galaxies, looking for something called redshift. Think of the Doppler effect with sound. An ambulance siren sounds high-pitched as it comes toward you. Waves are compressed. And low-pitched as it goes away. Waves are stretched. Light does something similar. If a galaxy is moving away from you, the light waves it emits get stretched. This stretching shifts the light toward the red end of the spectrum. Redshift. Another astronomer, Vesto Slipher, had already noticed that most of these galaxies were redshifted, meaning they were moving away. But Hubble had the missing piece: accurate distances. He plotted the data. A galaxy's distance on one axis, and how fast it was moving away on the other. A stunning pattern emerged, a direct, linear relationship that became known as Hubble's law. With very few exceptions, every galaxy was moving away from us. And the farther away a galaxy was, the faster it was moving away. For a second, consider the implications. This is exactly what you'd see if you were at the center of a cosmic explosion. Did this mean we were, after all, in a special, central spot? It was a tempting idea, but wrong. The genius of Hubble's law is that it works no matter which galaxy you're in. If we could teleport to a galaxy 1 billion light-years away and look out, we'd see the exact same thing. All other galaxies rushing away, with their speed proportional to their distance. This could only mean one thing. The galaxies weren't flying through space away from a central point. The very fabric of space itself was expanding. This was the solution to Olber's paradox. The night sky is dark because the universe has a finite age, and because the light from the most distant galaxies is stretched by this expansion, redshifted so much that it drops out of the visible spectrum. The universe wasn't a static container. It was a dynamic, evolving entity. And with that realization, the idea of an edge began to dissolve into absurdity. The raisin bread and the balloon. The aha moment. This is the conceptual heart of the matter, where we try to build a new intuition. Since space itself expanding is deeply weird, let's use a couple of classic analogies. First, the raisin bread. Imagine you mix up some dough and scatter raisins throughout it. Now, you put it in the oven. As the dough bakes, it expands. Pick any single raisin, call it the Milky Way raisin. From its perspective, as the dough, space, expands, every other raisin moves away from it. A raisin an inch away might end up 2 inches away. A raisin 3 inches away might end up 6 inches away. The farther the raisin, the more expanding dough there is between it and our raisin, so the faster it appears to recede. This perfectly explains Hubble's law. From any raisin's point of view, all other raisins are moving away, and the distant ones move faster. Crucially, are the raisins moving through the dough? No. They're being carried along by the expansion of the dough itself. And where's the center of the expansion? There isn't one. The center is the dough itself. Does the loaf have an edge? A real loaf has a crust, but for this to be accurate, you have to imagine an infinite loaf of raisin bread expanding everywhere, forever. The second analogy helps us picture how something can be finite but have no edge. The balloon. Imagine drawing dots on a deflated balloon. Each dot is a galaxy. As you blow up the balloon, the two-dimensional rubber surface our stand-in for the fabric of space stretches. A dot galaxy on the surface sees every other dot moving away, and farther dots recede faster. Again, Hubble's law is perfectly replicated. No dot is the center. Now for the key part. Does the 2D surface of the balloon have an edge? No. You can travel across it forever and never fall off. It's finite, it has a measurable surface area, but it's unbounded. Our universe might be the three-dimensional equivalent of that 2D surface. General relativity allows for space to be curved back on itself through a fourth dimension, creating a hypersphere. In that case, the universe would be finite in volume but have no boundary. But here's what we know. Our best measurements to date suggest the universe is flat on large scales. A flat universe is more like an infinite rubber sheet being stretched. While some data from the Planck satellite has suggested the universe could be curved and closed, this conflicts with many other observations, so most cosmologists currently lean towards a flat model. However, our observations can't yet definitively distinguish between a very slightly curved, finite universe and a perfectly flat, infinite one. But whether it's a finite hypersphere or an infinite flat plane, the takeaway is the same. In neither case is there an edge. So, what is it expanding into? We've arrived at the ultimate question, the one our intuition screams at us. What is the universe expanding into? The answer, both deeply unsatisfying and profoundly liberating, is nothing. The question itself is based on a false premise, like asking, what's north of the North Pole? It assumes the universe is an object expanding within a larger, pre-existing space. But the universe is not in space. The universe is space, and time, and all the matter and energy within it. There's no outside, because the concept of outside requires space for it to exist in. If there were some empty void beyond our universe, that void would, by definition, be part of our universe, too. Let that sink in. The expansion of the universe is the intrinsic stretching of space itself, everywhere. It's the continuous creation of distance between points. Think of the raisin bread. The expansion is a property of the dough. It doesn't need an oven to expand into. The expansion is happening internally. This is where we have to abandon our everyday experience. We're three-dimensional beings whose brains are built to understand objects moving within space. We don't have the hardware to truly visualize three-dimensional space itself expanding. It's a concept grasped through the language of math, specifically Einstein's theory of general relativity. Even before Hubble's discovery, a physicist named Alexander Friedmann solved Einstein's equations and found they didn't allow for a static universe. The universe had to be either expanding or contracting. Einstein himself disliked this so much that he added a cosmological constant to his equations to force a static universe, a move he later called his biggest blunder. History proved Friedmann right, and Hubble delivered the evidence. The distance between galaxies is increasing because more space is appearing between them. That's what's freaking me out. The foundation of reality isn't a fixed stage, it's a dynamic, growing fabric. Okay, quick pause. If your brain feels a little stretched right now, do me a solid and hit that like button. And if you're new here, consider subscribing. We dive into concepts like this all the time, and we're about to go even deeper, because even in a universe with no edge, there is a kind of boundary that affects us every single day. The edge we can see. So, if there's no physical wall, can we see forever? The answer is no, and the reason introduces another freaky concept: the observable universe. The universe may not have an edge in space, but it did have a beginning in time. The Big Bang, about 13.8 billion years ago. Light travels incredibly fast, but not instantly. The light from the Sun takes 8 minutes to reach us. The light from Proxima Centauri takes over 4 years. This creates a horizon in time, and therefore in space. Since the universe is 13.8 billion years old, the absolute farthest we can possibly see is the distance light has been able to travel in 13.8 billion years. Any object farther away than that has light that simply hasn't had enough time to reach us. This bubble of observation isn't a physical edge, it's a boundary defined by the cosmic speed limit and the age of the universe. This is the observable universe. Now, here comes another brain twister. You might think this means the observable universe has a radius of 13.8 billion light years. But it's much bigger. The current estimate for the radius is about 46.5 billion light years, making the total diameter a staggering 93 billion light years. How is that possible? The answer is the expansion of space we've been talking about. That 46.5 billion light-year figure is what's known as a comoving distance. Imagine a galaxy that emitted a photon toward us 13.8 billion years ago. Back then, it was much closer to us. But during the photon's 13.8 billion year journey, the space it was traveling through was continuously expanding. By the time that ancient photon finally reaches our telescopes today, the galaxy that sent it has been carried much, much farther away by cosmic expansion, all the way out to its current comoving distance of 46.5 billion light years. So, the edge of our observable universe isn't a wall. It's the surface in space-time from which light has taken the entire age of the universe to reach us. When we look at the cosmic microwave background, we are seeing that surface. We're literally looking at the infant universe. What's beyond it? The most logical assumption is just more universe. More galaxies, more clusters, looking roughly the same as ours. An alien in a galaxy 10 billion light years from us has its own observable universe, overlapping with ours but also including vast regions we will never see. It's a humbling thought. We're likely confined to seeing only a tiny fraction of an infinite reality. The fate of expansion. The story doesn't stop here. For the first several billion years after the Big Bang, the expansion was actually slowing down due to gravity. Cosmologists had two main scenarios. Either it would slow down enough to reverse into a big crunch, or it would slow down forever, leading to a cold, empty, big freeze. Then, in 1998, came another shock. Two teams of astronomers found that about 5 to 6 billion years ago, the expansion stopped slowing down. It started speeding up. The expansion is accelerating. Something is fighting gravity, pushing space-time apart. This mystery was given a name: dark energy. The leading theory is that it's an intrinsic energy of the vacuum of space itself, a kind of repulsive gravity. As space expands, more of this energy appears, which pushes space to expand even faster in a runaway loop. However, its true nature remains one of the biggest mysteries in physics. These calculations, which are based on the standard lambda CDM, lambda cold dark matter, model, suggest dark energy makes up about 68% of the universe, with dark matter making up another 27%. All the normal matter, everything we can see, is less than 5%. But the plot has thickened. As of 2026, there's a major unresolved issue in cosmology known as the Hubble tension. Measurements of the expansion rate using local methods, like observing nearby supernovae, give a different value than measurements using distant methods, like studying the cosmic microwave background. This discrepancy suggests that our standard lambda CDM model might be incomplete or even wrong. This accelerating expansion, whatever its true cause, has profound consequences. Galaxies not gravitationally bound to us are being pushed away so fast that, eventually, their light will no longer be able to reach us. Over trillions of years, they will vanish from our sky, leaving future astronomers to look out on a dark, empty void, perhaps wrongly concluding their own supergalaxy is all that ever was. So here we are, adrift in a cosmos with no edge and no center. A universe that began 13.8 billion years ago and is now expanding at an accelerating and contested rate, driven by a mysterious dark energy we don't understand. We live inside an observational bubble, seeing only a piece of a reality that may be infinite, watching as distant galaxies are carried away from us forever. It is, without a doubt, unsettling. It violates our common sense, which was forged on the plains of Africa, not in the crucible of intergalactic space. It's okay that it's freaking me out. It should be freaking you out, too. It means we're paying attention. But it's also beautiful. It replaces our simple picture of a contained universe with something far grander and more mysterious. We've journeyed from a cozy, Earth-centered cosmos to an accelerating, and ultimately lonely one. The universe isn't a box. It's a process. And we are just along for the ride. This leaves us with a final, haunting question. The standard model predicts a future where the accelerating expansion stretches everything into a cold, dark nothingness, the Big Freeze. But given the cracks appearing in that model, what's the real ending? Some recent, more speculative models based on new data even suggest the cosmological constant could be negative, meaning this expansion might one day reverse, pulling everything back into a big crunch, about 20 billion years from now. If you want to explore that terrifying and fascinating question with me in a future video, make sure you're subscribed. The universe is full of mysteries, and we've only just scratched the surface. Thanks for getting freaked out with me today. And as always, keep looking up. The cosmic illusion that tricks every observer. When you look up at the vast, silent canvas of the cosmos, doesn't it feel like you're at the very center of it all? It's a feeling that's both humbling and, in a weird way, pretty empowering. From our tiny little home here on Earth, every distant galaxy, no matter which way we look, appears to be rushing away from us. It's as if the entire universe is one spectacular firework display, and we're standing at the exact point of the explosion. The cosmos itself seems to be sending us a message, loud and clear. You are special. You are the center. But that feeling, that deep, gut instinct telling us we're the star of the show, is a trick. It's a profound and beautiful cosmic illusion, woven right into the fabric of space and time. And it's an illusion that every single observer, on every planet, in every galaxy across the entire universe, experiences. Once you get why this illusion happens, the way you see your place in the universe and the universe itself will never be the same. This isn't just about astronomy. It's about shifting your entire perspective on reality. An accidental discovery. Our story starts not with a philosopher, but with an astronomer who was just trying to map the night sky. Back in the 1920s, a quiet, meticulous observer named Edwin Hubble was tackling one of the biggest questions in the history of science. Armed with the world's most powerful telescope at the time, he wanted to settle a huge debate. Were those faint, fuzzy patches of light called spiral nebulae just clouds inside our own Milky Way, or were they entire, island universes, all on their own? Through painstaking work, Hubble found a special kind of star in the Andromeda Nebula, a Cepheid variable. These stars are amazing because they pulse, and the speed of that pulse is directly tied to how bright they truly are. By timing the pulse, Hubble could figure out the star's real brightness. Then, by comparing that to how dim it looked from Earth, he could calculate its distance. The number he came up with was staggering. His first estimate put Andromeda at about 900,000 light-years away, far outside the known limits of the Milky Way. In that one moment, our known universe got 100 times bigger. Those smudges weren't in our backyard. They were entire galaxies, each with billions of stars. But Hubble was just getting started. Working with his assistant Milton Humason, he didn't just measure how far away these galaxies were, he analyzed their light. They looked at the light spectrum, which acts like a cosmic barcode, revealing the elements inside a galaxy. And they found something consistent and really weird. For almost every galaxy, the spectral lines were shifted. They weren't where they should be. They were all shifted toward the asterisk red end of the spectrum. This redshift has a clear explanation: the Doppler effect. It's the same reason a siren sounds high-pitched as it comes toward you and low-pitched as it goes away. Light from something moving toward us gets compressed, shifting it toward the blue end of the spectrum. Light from something moving away gets stretched, shifting it toward the red. What Hubble saw was undeniable. Almost every single galaxy, in every direction, was redshifted. They were all moving away from us. That was incredible enough. But then Hubble made his second, even bigger discovery. He plotted the data on a simple graph. On one axis, a galaxy's distance, and on the other, the speed it was moving away. The result was a straight line. The relationship was crystal clear. The farther away a galaxy was, the faster it was receding. This became known as Hubble's law. A galaxy 10 million light-years away was moving 10 times faster than a galaxy 1 million light-years away. Imagine standing on a street corner and seeing every single person running away from you. And not just that the people a block away are running faster than the people on your block, and the people 10 blocks away are running 10 times faster. What's the only logical conclusion? You must be at the exact spot where a starting pistol just fired. The evidence seemed irrefutable. The universe was expanding, and we were at the absolute center of it all. The illusion takes shape. For a minute there, it seemed like science had given humanity its crown back. After Copernicus kicked Earth out of the center of the solar system, and we later found out our sun is just an average star in a boring suburb of the Milky Way, Hubble's data seemed to make us special again. We were, it appeared, the origin point of the entire cosmos. But this is where the story takes a sharp turn, and the obvious answer crumbles to reveal something much deeper and more elegant. That feeling of being at the center? It's an illusion. A powerful one, sure, but an illusion all the same. Here's the mind-bending part. An observer in any galaxy would see the exact same thing. Let that sink in for a second. If you were on a planet in a galaxy a billion light-years from here, you'd look out at your sky and discover the very same law that Hubble did. You'd see every other galaxy rushing away from you. And you'd find that the farther a galaxy is from you, the faster it's moving away. You, too, would feel that undeniable, evidence-backed certainty that you were at the center of the universe. This simple, powerful idea shatters the illusion. It means there is no center. Or, maybe a better way to think about it is that everywhere is the center. That feeling of being the origin point isn't special to our location. It's a universal property of the expansion itself. Understanding how that's possible is the key to this cosmic trick. It's not a flaw in our telescopes. It's a fundamental consequence of how the universe works, and it forces us to completely rethink what we think we know about space and distance. The universe isn't a bomb exploding into an empty room. It's something much, much stranger. The first great analogy, the raisin bread universe. To start wrapping our heads around this, let's ditch the explosion image and think about something more humble. A loaf of raisin bread baking in an oven. This simple thought experiment is one of the best ways to understand cosmic expansion. Imagine a ball of unbaked bread dough filled with raisins. Each raisin is a galaxy, and the dough is the fabric of space itself. Now, pop that loaf in the oven and watch it rise. As the dough expands, what happens to the raisins? The key thing here is that the raisins aren't moving through the dough. They aren't tiny raisin spaceships zipping around. They're just being carried along as the dough space itself expands. The raisins stay the same size, just like galaxies don't expand. But the space between them grows. Now, let's look at this from the perspective of one raisin. We'll call it the Milky Way raisin. What does it see? It looks at a nearby raisin, say, an inch away. As the dough doubles in size, that neighbor is now 2 inches away. It has moved 1 inch in that time. But now look at a raisin that started 3 inches away. When the dough doubles, it's now 6 inches away. It has moved 3 inches in the same amount of time. From our Milky Way raisin's point of view, every other raisin is moving away. And more importantly, the speed they seem to be moving is directly proportional to their distance. The raisin that was 3 times farther away looks like it moved 3 times faster. And just like that, you've got Hubble's law in a loaf of bread. But here's the kicker. Now, imagine you're a different raisin. Any other raisin in the loaf. From its perspective, what's happening? It sees the Milky Way raisin moving away. It sees all the other raisins moving away. And just like before, it sees that the farther away a raisin is, the faster it recedes. Every single raisin in the loaf would have the identical experience. The illusion of being the stationary center of the expansion. There is no central raisin. The center of the expansion isn't in the dough at all. The expansion is happening everywhere in the dough at once. This is what's wrong with our first guess about Hubble's data. We assumed galaxies were like shrapnel flying through a static, pre-existing space. The raisin bread tells us that's the wrong way to think. It's not the galaxies moving through space, but the space between the galaxies that is stretching. The Big Bang wasn't an explosion in space. It was the beginning of the expansion of space itself. The second great analogy. The expanding balloon. The raisin bread is great for 3 dimensions, but to get another key part of the cosmic illusion, the shape of space, we turn to another classic. Dots on the surface of a balloon. Imagine you have a deflated balloon. Draw a bunch of dots on it. These are our galaxies. Pick one and call it the Milky Way. Now, start blowing up the balloon. As it inflates, the rubber surface stretches, and every dot sees every other dot moving away from it. And just like before, the farther dots appear to move away faster. You've perfectly replicated Hubble's law again. If you were a 2-dimensional creature living on the balloon's surface, you'd be totally convinced you were the center of your universe. You'd do the science, and you'd prove it. And your friend on another galaxy would do the exact same experiments and come to the same self-centered conclusion. The power of this analogy is what it tells us about centers and edges. Ask yourself, where is the center of the expansion on the surface of the balloon? There isn't one. The expansion is happening all over the 2D surface at once. You can't point to a spot on the rubber and say, it all started here. Now, you might be thinking, but the center is obviously inside the balloon. And you'd be right. But that center exists in the 3rd dimension, a dimension the 2D creatures on the surface can't see or point to. This is the mind-bending leap we have to make. When we ask, where's the center of the universe? We're assuming a center exists in our 3 dimensions. The balloon suggests that just like there's no center on the 2D surface, there's no center in our 3D space. If our universe has a center, it might be in a fourth spatial dimension we can't even imagine. From our limited view, the expansion just happens everywhere. The balloon also helps with the question, what is the universe expanding into? A balloon expands into the air in the room. But the universe is, by definition, everything. There's no room outside of it. For the 2D creatures, their reality is the curved rubber surface. There is no outside for them. If they travel in one direction long enough on a finite balloon, they'll end up right back where they started. Their universe is finite, but it has no edge. This is how cosmologists think our own universe might work. It might be finite, but have no boundary. The question, what is it expanding into, becomes meaningless. Space isn't a container, it's the thing that's growing. The illusion works because we're stuck inside this expanding fabric, unable to see the whole picture from an outside. That doesn't exist. The fabric of spacetime and the nature of redshift. With those analogies in our back pocket, we can now tackle the core physics. The most important idea to grasp is this. The redshift we see from distant galaxies isn't really a form of motion through space, but a result of the expansion of space. This is a really important, and kinda tricky, distinction. When we talk about motion, we mean a car driving down a road. That's called peculiar velocity. And galaxies do have that. Andromeda, for example, is actually moving towards us because of gravity. On local scales, gravity is strong enough to beat the expansion. But when we look at really distant galaxies, beyond our local neighborhood, we see something else. The redshift from them isn't a regular Doppler shift. It's a cosmological redshift. Here's how it works. A photon of light is emitted from a galaxy billions of light years away. While that photon is traveling, the universe itself is expanding. The space it's moving through is literally stretching. As the fabric of space stretches, the light wave within it gets stretched out too. Its wavelength gets longer. By the time that photon finally reaches our telescopes, its wavelength has been stretched significantly toward the red end of the spectrum. The longer its trip, the more space has expanded, and the more its light has been redshifted. The galaxy that sent the photon isn't necessarily moving in the normal sense. It's more like two people standing still on a giant, stretching rubber sheet. They aren't walking away from each other, but the distance between them grows. The redshift is a direct record of how much the universe has expanded since that light started its journey. This also clears up a huge paradox. Hubble's law implies that if you look far enough away, galaxies are receding from us faster than the speed of light. This sounds like it breaks Einstein's golden rule, but it doesn't. That cosmic speed limit applies to motion through space. It doesn't apply to the expansion of space itself. The space between us and a very distant galaxy can stretch so much that the total distance increases faster than light can travel. The galaxy isn't breaking the speed limit locally. It's just that all the expanding space between us adds up. It's like trying to swim up a river that's flowing faster than you can swim. You're moving through the water, but the water itself is carrying you backward relative to the shore. This is the cosmic illusion at its peak. We're trapped in our own viewpoint, interpreting a universal stretching of space-time as things simply flying away from us. The cosmological principle, the rules of the game. For this illusion to work for everyone, the universe has to play by some ground rules. If some parts were lumpy and dense while others were empty, or if it expanded faster in one direction, that would create special places, and the illusion would break. Luckily, when we look at the universe on the largest scales, it seems to follow a very consistent set of rules. This is called the cosmological principle, and it has two main parts: homogeneity and isotropy. First, homogeneity. This just means that on a big enough scale, the universe is the same everywhere. Obviously, that's not true up close. We have planets, stars, and huge empty voids. But if you zoom out far enough, hundreds of millions of light years, it all averages out. A giant cube of the universe from our neighborhood would look statistically the same as one from billions of light years away. Second, isotropy. This means the universe looks the same in every direction. Again, on the largest scales. From Earth, looking toward the Virgo cluster is very different from looking at the Boötes void. But if you average out the whole sky, no one direction is special. The best evidence for this comes from the cosmic microwave background, CMB. This is the faint afterglow of the Big Bang. When we look at the CMB, we see a snapshot of the universe when it was just 380,000 years old. And it's shockingly uniform. The temperature of this radiation is the same in every direction to a precision of about 1 part in 100,000. This incredible smoothness tells us the universe started off incredibly homogeneous and isotropic. Together, these principles mean that our place in the universe is in no way special or privileged. And if our place isn't special, then a universe that's the same everywhere, homogeneous, and in every direction, isotropic, must create the illusion we see. It can't have a true center, because that would be a special place. It can't have an edge, because that would be a special direction. If it's expanding, it must expand everywhere at once. And if that's true, then any observer, anywhere, will see themselves as the center of their own observable bubble. The illusion isn't a coincidence. It's a logical necessity. The view from another galaxy. We've talked about this hypothetically, so let's make it real. Imagine we have a ship that can travel instantly. We punch in the coordinates for a galaxy on the far side of our observable universe. Let's call it ZG1, a cool 10 billion light years from home. We hit the button and poof, we're on a planet in ZG1. The sky is filled with alien stars, but the basics are the same. We want to find home, so we point our telescope back in the direction of the Milky Way. It's just a faint smudge. We take a reading of its light. The result? It's dramatically redshifted. From our new home, the Milky Way is racing away from us at an unbelievable speed. Now we start looking around. We pick a galaxy that, from Earth, was even farther away. From here in ZG1, it's much closer, just in a different direction. We measure its light. It's redshifted. It's moving away. We look in the complete opposite direction, at a galaxy that was on the other side of the sky from Earth. Its light is also redshifted. It's also flying away. Imagine we spend a year doing a full survey, just like Hubble. We measure the distances and redshifts for hundreds of galaxies visible from ZG1. We plot the data. And what do we find? A perfect straight line. The farther a galaxy is from us, here in ZG1, the faster it's receding. The conclusion is inescapable. The evidence is overwhelming. We, here on this planet in the ZG1 galaxy, are the center of the universe. This is the cosmic illusion in its full, deceptive glory. The laws of physics themselves conspire to create this personal, egocentric story for every single observer. It's a story the universe tells everyone, and for everyone, the story is true from their limited perspective. To be at the center of the universe isn't a unique address, it's the default condition of existence. And by understanding that, we don't lose our specialness. We realize we share this special condition with everyone, everywhere. A new perspective. We started with a simple observation that made us feel like the masters of the cosmos. Everything is running away from us. But as we peeled back the layers, the illusion was revealed. We learned from the raisin bread and the balloon that the same law could be true for every observer in a uniformly expanding space. We aren't at the center of a cosmic explosion. We're just passengers on an expanding fabric of spacetime. We discovered that redshift is a record of space itself stretching over billions of years, which solves the paradox of galaxies receding faster than light. And we saw how the cosmological principle, the idea that the universe is the same everywhere and in all directions, makes this illusion a logical necessity for everyone. Understanding this does something profound. The initial, egotistical feeling of being the center is replaced by something far more humbling and beautiful. We're not the unique origin point. We're an integral part of a vast, interconnected whole. Our experience isn't unique, it's universal. An alien astronomer a billion light years away looks at their sky and feels the exact same sense of centrality we do. This is the ultimate fulfillment of the Copernican revolution. We're not just removed from the center of the solar system or the galaxy. We're removed from the center of the universe itself, because no such center exists in any way we can truly grasp. If this journey has expanded your mind, consider subscribing. We dive into big questions like this every week. And let me know in the comments. How does understanding this illusion change how you view your place in the universe? The next time you look up at the night sky, remember the illusion? The universe isn't fleeing from you. It's simply growing. And in that growth, it gives every observer, on every world, a front row seat to the greatest show in existence. You aren't the center of the universe. You are a center of the universe. And in that shared status, we find a deeper connection to the cosmos than any privileged position could ever offer. You aren't just an observer of the universe. You are the universe, observing itself. Why your speed is a complete illusion. You think you know how fast you're going. It's one of the most immediate, tangible numbers in our lives. You glance at a dashboard, feel the wind in your hair, watch the world blur outside a window. These things give us a sense of speed, a concrete value for our motion. 70 miles per hour. 30 kilometers an hour. 5 miles per hour. These numbers feel solid, absolute, real. But what if I told you that every single one of those numbers, from a lazy walking pace to the scream of a fighter jet, is a complete illusion? What if the very idea of a single, true, speed is a ghost, a phantom that physicists have chased for centuries, only to find it doesn't exist? This isn't a metaphor. It's a fundamental truth about the very fabric of our reality. The speed you feel, the speed you measure, is a story. And like any good story, it only makes sense from a certain point of view. Change your point of view, and the story and the speed changes completely. In the next few minutes, we're going to unravel your perception of motion. We'll start on a familiar highway, where the rules of speed seem simple. But then we're going to take that same principle, that same simple illusion, and scale it up. Past planes, past planets, past our own sun, all the way to the edge of the observable universe. Because the secret to understanding your place in a constantly expanding cosmos is hidden in the simple act of one car passing another. Get ready, because the solid ground of speed is about to dissolve right under your feet. You're driving down the highway at 70 miles per hour. That number feels absolute. It's glowing on your speedometer, a testament to your progress. But it's an illusion. Because right now, you are also on a planet that is spinning on its axis at over 1,000 miles per hour. And that planet is hurtling around the sun at a staggering 67,000 miles per hour. And our entire solar system is being dragged around the center of the Milky Way galaxy at a mind-numbing 514,000 miles per hour. And the galaxy itself? It's part of a colossal cosmic flow, carrying you through the universe at over 800,000 miles per hour relative to the faint afterglow of the Big Bang. So, which one is your real speed? 70 miles per hour? Or 800,000? The truth is, none of them. And all of them. By the end of this video, you'll understand why that baffling fact is the key to your true place in the universe. The everyday illusion. Deconstructing the highway. Let's start somewhere familiar. A car on a highway. The problem of speed is really a problem of perception. Our brains are wired for survival, which means they're local machines. They interpret the world based on immediate context. When you're in a car, your context is the car and its relationship to the road. The speedometer measures exactly that one relationship. How fast the wheels turn against the asphalt. It gives you a number, say, 60 miles per hour. And to you, that number feels like a fact about you. I am going 60. But this is where the illusion begins. That number isn't a property of you. It's a property of a asterisk relationship. The moment you introduce another object into the story, the number can change. Physicists call this your asterisk frame of reference. It's what you're measuring your speed against. On the highway, the asphalt is your default frame of reference. But it's not the only one. Imagine a truck in the lane next to you, also going exactly 60 miles per hour. You glance over. The driver is right there. From your perspective, that massive truck is perfectly still. It just hangs in the air beside you. Relative to the truck's frame of reference, your speed is zero. Nothing. So, are you moving at 60, or are you moving at 0? Both are true. It just depends on what you ask. Now, let's say you hold your steady 60, but a sports car zips past you at 70. From your seat, it doesn't look like a 70 mph blur. It seems to be pulling away from you pretty slowly, at just 10 miles per hour. And in your reference frame, that's exactly its speed. To a state trooper parked on the shoulder, however, that sports car is a 70 mph projectile, and you're not far behind. Let's flip it one more time. You're still cruising east at 60. A car in the opposite lane is heading west, also at 60. From your point of view, this isn't a slow drift. It's a violent, instantaneous event. The closing speed between you two is 120 miles per hour. The distance evaporates in a flash. Yet to the driver behind that car, it's just another vehicle doing 60. This is the heart of what's known as Galilean relativity, described by Galileo long before Einstein. He imagined being in the windowless cabin of a ship on a smooth sea. He realized that if you dropped a ball, it would fall straight down. Flies would buzz around normally. Every experiment would give the same results as if the ship were tied to the dock. There'd be no sensation of motion. The laws of physics are the same for anything moving at a constant velocity. There's no master reference frame. There is no absolute state of rest. The ground only feels still because we're standing on it. It's just another frame of reference, no more special than your car. The feeling of being motionless is the biggest illusion of all. It just means you're moving at the same speed as your immediate surroundings. Expanding the playground. From highways to planets. So, speed is relative on a highway. A neat trick, right? But this isn't just a quirk of perception. It's a fundamental rule of the universe. It's why we don't feel our own planet hurtling through the void. What happens when we zoom out, when our frame of reference is no longer a car, but the entire Earth? Right now, you probably feel like you're sitting still. You're not. The Earth is a sphere, and it rotates on its axis once every 24 hours. If you're near the equator, that means you're moving at over 1,000 miles per hour. Why don't you feel it? Why isn't there 1,000-mile-per-hour wind ripping you off your feet? It's the same reason the ball drops straight in Galileo's ship. You, your chair, the building around you, and the entire blanket of Earth's atmosphere are all moving together as one big reference frame. There's no relative motion between you and the air, so there's no wind. You are, quite literally, inside the cabin of Spaceship Earth. Your speed relative to the ground is 0, so you feel at rest, even while you're breaking the sound barrier. This has real, high-stakes consequences. Take an airplane. A pilot has to deal with multiple frames of reference at once. The plane's engines push it forward relative to the air. That's its airspeed. But the air itself is often moving relative to the ground. That's what we call wind. The plane's actual path over the ground, its ground speed, is a combination of the two. Imagine a pilot wants to fly north at 100 miles per hour, but there's a 25 mile per hour wind blowing from the west. If they point the plane's nose due north, they won't go north. They'll be pushed sideways, drifting off to the northeast. To actually travel north, the pilot has to perform a clever trick of relative motion. They have to point the plane slightly northwest, crabbing into the wind to cancel out its push. They are using one velocity to negate another, all to control their motion relative to a third frame of reference, the ground. Let's scale this up again, to the cosmic level. Our Earth isn't just spinning. It's also in a much grander orbit around the Sun, rocketing through space at about 67,000 miles per hour, or nearly 30 kilometers every single second. Think about that. In the time it takes to snap your fingers, you've traveled about 19 miles. And yet, you feel nothing. Why? Same reason. The entire solar system, the Sun, the planets, you are all falling around the Sun together. We are all in the same, gravitational cabin, so there is no relative motion to feel. There is no cosmic wind to push against our faces. Our reference frame has become the Sun, and within that frame, we're just tracing a predictable path once a year. The 67,000 mile per hour journey is completely imperceptible because our local environment is coming along for the ride. The cosmic jolt. Einstein enters the chat. So far, the rules have felt pretty intuitive. Velocities are relative. You add them, you subtract them. A person walking on a train adds their speed to the train's speed. Simple. This is the world of Galileo and Isaac Newton. It's a clockwork universe where space is a fixed stage and time flows the same for everyone. But at the turn of the 20th century, one stubborn fact about light started to unravel this tidy picture. And figuring it out required a mind like Albert Einstein's to completely reboot our understanding of space and time. Here's the problem that broke classical physics. Let's go back to our train. Imagine it's a futuristic maglev train moving at an impossibly fast, constant speed, say, half the speed of light. You turn on a flashlight and point it towards the front of the train. According to everything we've said so far, this is a simple addition problem. For someone on the platform watching the train fly by, the light beam's speed should be the speed of the train plus the speed of light. Right? Wrong. That's not what happens. Experiments in the late 19th century had already shown something baffling. The speed of light was the same, no matter how the source or the observer was moving. The person on the platform measures your flashlight beam and finds it moving at exactly the speed of light, c. Not 1.5 c. Just c. But here's where it gets even weirder. You, on the train, also measure the speed of the light from your flashlight. You would also measure its speed to be exactly c. This is the bombshell. This is the core of Einstein's special theory of relativity. The speed of light in a vacuum is the same for all observers. It's an absolute constant. This one idea shatters Galilean relativity. Because if the speed of light refuses to change, something else must. And that something else, Einstein realized, was space and time. To keep the speed of light constant for everyone, reality itself becomes flexible. For someone moving at high speed, time itself literally slows down, and space itself literally contracts in the direction of motion. From the perspective of the person on the platform, your clock on the fast-moving train is ticking slower than theirs. Your train car is physically shorter than it would be at rest. And from your perspective on the train? You see the platform as the moving object. So from your point of view, it's the platform dwellers' clock that is ticking slower, and their world that has gotten shorter. Both views are equally valid. There is no privileged observer. The consequence is profound. It demolishes the idea of a universal now. The idea that two events are simultaneous is also relative. This is why you can never find an absolute rest frame. If there were some fixed, stationary grid in the universe, you could measure your speed relative to it. But special relativity says that since the speed of light gives you the same answer no matter how you're moving, you can never know your true motion. Every frame of reference is just as valid as any other. Einstein didn't just show that speed was relative. He showed that space and time are relative, too, all to serve one absolute master. The speed of light. The ultimate reference frame? The expanding universe. So, Einstein tells us there's no universal, still point, no cosmic anchor. This creates a new puzzle. If there's no absolute background, what do we measure the biggest motions against? When astronomers say the Andromeda galaxy is hurtling towards us, what is it moving relative to? It turns out, the universe itself provides an answer, but it's stranger and more wonderful than a simple, static grid. In the 1920s, Edwin Hubble discovered that the light from distant galaxies was almost always redshifted. This is a cosmic Doppler effect. It meant those galaxies were moving away from us. But the truly shocking part was that the farther away a galaxy was, the faster it was receding. This doesn't mean we're at the center of a cosmic explosion. The best analogy is a loaf of raisin bread dough rising in an oven. Imagine the dough is the fabric of space, and the raisins are galaxies. As the dough expands, every raisin sees every other raisin moving away from it. A raisin 1 inch away moves a certain speed, but a raisin 2 inches away appears to move twice as fast, because there's twice as much expanding dough between them. This is the key to cosmic expansion. Galaxies aren't flying through space. Space itself is expanding, carrying the galaxies along for the ride. There is no center. An alien astronomer in a galaxy a billion light-years away sees the exact same thing we do. So, is there any way to define a universal background? Amazingly, yes. The universe has gifted us one. It's called the Cosmic Microwave Background or CMB. The CMB is the oldest light in the universe, the faint afterglow of the Big Bang itself. It's a bath of microwave radiation that fills all of space. And it is incredibly uniform. No matter where we look, it's almost the exact same temperature. A frigid 2.7 Kelvin. Almost. When we measure the CMB with incredible precision, we find a tiny, distinct pattern. In one direction, towards the constellation Leo, the CMB is ever so slightly hotter, its light is blue shifted. In the exact opposite direction, it's ever so slightly colder, red shifted. This is our motion, written across the entire sky. It's the ultimate Doppler effect. We are moving towards the hotter part of the CMB and away from the colder part. By measuring this tiny temperature difference, we can calculate our speed relative to this ancient light. This is the closest thing we have to a rest frame of the universe. And what is that speed? When we add up all our local motions and measure our collective velocity against this cosmic backdrop, we find our solar system is being carried along at about 370 kilometers per second, or roughly 828,000 miles per hour. So, is that it? Is 828,000 miles per hour our one true speed? No. The CMB is a wonderfully convenient reference frame, but it's not absolute. It's just the reference frame in which the Big Bang's afterglow is uniform. It's like measuring your speed relative to the air on a perfectly still day. It's a natural reference, but it doesn't make the asphalt on the highway any less valid for the trooper writing you a ticket. It's a cosmologically preferred frame, but not a physically absolute one. What this all means for you? Let's come back to where we started. That feeling of motion, that number on your dashboard. We called it an illusion. The 70 miles per hour on your speedometer isn't false. It's a perfectly real, measurable, and important fact about the relationship between your car and the patch of Earth it's rolling over. The Earth's orbital speed of 67,000 miles per hour is also real. It's a solar truth, describing the gravitational dance between our planet and its star. And our solar system's staggering velocity of over 800,000 miles per hour relative to the cosmic microwave background? That is a cosmic truth, a statement about our motion with respect to the oldest thing we can see. None of these speeds is the real one. All of them are. They are different answers to different questions. How fast am I going? Is an incomplete question. The complete question is always, how fast am I going relative to what? This is the ultimate takeaway. You don't have a speed. Speed isn't a property of an object, like its mass. It's a property of a asterisk relationship between objects. Motion is a story that requires at least two characters. Without a reference point, the concept is meaningless. So, the next time you find yourself sitting, perfectly still, in a chair, on a park bench, take a moment to appreciate the profound illusion of that stillness. You are on a planet spinning at 1,000 miles an hour, orbiting a star at 67,000 miles an hour, sweeping around a galaxy at 500,000 miles an hour, and hurtling through the expanding universe at over 800,000 miles an hour. You aren't an object at rest. You are a symphony of motions, a cascade of nested reference frames, all happening at once. And understanding this doesn't make you feel small. It makes you realize that you are fundamentally and inextricably connected to everything else. From the asphalt under your tires to the most distant galaxy, you are part of a universal dance, bound by the beautiful, inescapable laws of relativity. Your speed isn't just a number. It's your relationship with the rest of the universe. If this new perspective on the universe blew your mind, just imagine what else is hiding in plain sight. We explore these kinds of questions every week, peeling back the layers of reality to see what makes the cosmos tick. So if you want to keep challenging your perceptions, make sure you hit that subscribe button. And we have a question for you. Let us know in the comments, what reference frame are you in right now? The Big Bang left a glitch that challenges Einstein. There is no such thing as standing still. Right now, you're hurtling through space at a speed you can barely comprehend. You're on a planet that's spinning at over 1,000 kilometers an hour. That planet is orbiting a star at 30 kilometers a second. That star is screaming around the center of a galaxy at 220 kilometers a second. And that galaxy? It's being pulled through the universe at over 600 kilometers per second. It's motion, on top of motion, on top of motion. And yet, what if I told you that all that movement, all that cosmic chaos, could be measured against a single, immovable benchmark? A true north for the entire universe. A place of absolute, cosmic rest. The very idea seems to fly in the face of the last century of physics, directly challenging the foundational principles of Albert Einstein himself. Because if there is an absolute rest in the universe, then our entire understanding of reality has a fundamental glitch. A ghost in the machine, left over from the very first moments of creation. The idea that all motion is relative is one of the most profound concepts in modern science. It's the bedrock of Einstein's theory of relativity. Think about it. If you're on a perfectly smooth train with no windows, you have no way of knowing if you're moving at 100 kilometers an hour or standing perfectly still. Every experiment you could do, every ball you could toss in the air, would behave in exactly the same way. The laws of physics don't care about your velocity, as long as it's constant. There's no special, privileged, or absolute frame of reference to judge all others from. This is the principle of relativity. It's elegant. It's powerful. And for over 100 years, it has been the law of the land. But the universe, it seems, has a long memory. Hidden in the oldest echoes of the Big Bang, there is a signal. A faint glow that fills every corner of space. It's the oldest light in the cosmos, a relic from when the universe was just an infant. And this ancient light seems to be telling us something completely different. It seems to provide exactly what Einstein said couldn't exist. A universal frame of reference. A cosmic rest frame. This is the story of a paradox at the heart of cosmology. It's a tension between the universe as our theories say it should be, and the universe as we actually see it. It's a story about a faint, cold glow called the cosmic microwave background, and how it acts as a universal speedometer, letting us clock our exact speed through the cosmos. But it's also the story of a deep and troubling anomaly, a glitch in our models that recent data has only made more confusing. An anomaly suggesting that the very foundation of our cosmology, the idea that the universe is the same in all directions, might be wrong. We're going to explore this cosmic paradox, what it means for our place in the universe, and whether this glitch is a crack in Einstein's masterpiece, or a clue to some new, deeper physics we have yet to discover. The expanding universe and the problem of rest. So, why is a cosmic rest frame such a revolutionary idea? To get it, we first need to appreciate the universe Einstein was trying to describe. For most of human history, we assumed the stars were fixed points in an eternal, unchanging void. Newton pictured a universe built on a rigid, absolute grid of space and time. In his world, you could, in principle, figure out your absolute position and your absolute motion. It was a clockwork universe, neat and predictable. Then, in the early 20th century, two things happened that shattered this picture. First, Einstein came along. His special theory of relativity in 1905 demolished the idea of absolute space and time. He showed that they are woven together into a single fabric spacetime, and your experience of it depends entirely on your motion. Two observers moving relative to each other will measure time and distance differently. There is no master clock, no universal ruler. All non-accelerating frames of reference are equal. This was a radical departure. A universe with no center, no edge, and no predefined grid. The second shock came in the 1920s, thanks to Edwin Hubble. Peering through the era's most powerful telescopes, Hubble made a startling discovery. He wasn't just seeing stars in our own Milky Way. He was seeing entire other galaxies, vast islands of stars like our own. And almost all of them were rushing away from us. Even weirder, the farther away a galaxy was, the faster it was receding. This was the first proof of the expanding universe. But it's a strange kind of expansion. It's not like a bomb going off, with everything flying out from a single point. That would mean there's a center, which would violate Einstein's new view of the cosmos. Instead, the very fabric of spacetime itself is stretching. The classic analogy is a balloon with dots drawn on it. As you inflate the balloon, every dot moves away from every other dot. No single dot is the center of the expansion. From the perspective of any dot, all the others are moving away. This is our modern picture of the cosmos. A universe born from a hot, dense state, the Big Bang, that has been expanding and cooling ever since. Galaxies aren't flying through space. They're being carried along by the expansion of space. And this brings us back to the problem. If everything is moving away from everything else, what does it even mean to be at rest? Relative to what? You can say you're at rest relative to the Earth, but the Earth is moving. Relative to the Sun? The Sun is moving. Relative to the center of the Milky Way? Our whole galaxy is moving. In an expanding universe ruled by relativity, there seems to be no anchor, no fundamental benchmark. It's like being on a raft in the middle of a boundless ocean with no land in sight. You see other rafts drifting away, but you have no idea if you're drifting, or they are, or if everyone is. You have no cosmic shoreline to measure your speed against. According to Einstein, this isn't a problem to be solved. It's a basic feature of reality. There is no shoreline. But what if there was? What if, hidden in the fabric of this expanding cosmos, was a faint signal from the moment of its birth? A signal so old and fundamental that it isn't moving with any galaxy or cluster, but instead fills the entire universe, acting as the ultimate backdrop. A signal that could finally let us answer the question: how fast are we really moving? The echo of creation. What is the CMB? To find this cosmic shoreline, we have to travel back in time. Way back. Almost 13.8 billion years. In the first moments after the Big Bang, the universe was an unimaginably hot, dense inferno, a seething, opaque soup of fundamental particles and intense radiation. For the first 380,000 years, the universe was in a state of cosmic lockdown. The temperature was so extreme that atoms couldn't form. Electrons, instead of being bound to atomic nuclei, zipped around freely in a roiling plasma. This sea of electrons acted like a dense fog. Light particles, called photons, couldn't travel more than a few steps without slamming into an electron and being sent off in a random direction. The universe was completely opaque. If you could have been there, you'd have seen nothing but a blinding, uniform wall of light, like being inside the sun. But as the universe kept expanding, it also cooled. And when the temperature dropped to about 3,000 Kelvin, something magical happened. It hit a critical threshold. Suddenly, it was cool enough for electrons to be captured by protons and helium nuclei, forming the first stable, neutral atoms. This event is known as recombination, or decoupling. The effect was instantaneous. With the free electrons now locked up inside atoms, the universe's dense fog suddenly lifted. The photons, which had been trapped in an endless game of pinball, were now free to travel in straight lines, unimpeded, across the cosmos. For the first time, the universe became transparent. The light that was released in that moment is what we now call the cosmic microwave background, or CMB. These are the very same photons, the oldest light in the universe, that have been streaming through space for 13.8 billion years. They are, quite literally, the afterglow of creation, the faint echo of the Big Bang. As the universe expanded, the wavelength of this ancient light has been stretched out, just like the sound of a receding siren is stretched to a lower pitch. This cosmic red shifting has cooled the light from its original fiery 3,000 Kelvin to a mere whisper. Today, the CMB has a temperature of just about 273 Kelvin, less than 3 degrees above absolute zero. This is why we detect it not as visible light, but as microwaves. The prediction and discovery of the CMB was a monumental triumph for the Big Bang theory. It was the smoking gun. And it has some truly remarkable properties. First, it's everywhere. No matter where you point a radio telescope, you detect this faint, persistent microwave hiss. It comes from every direction with almost perfect uniformity, isotropic to about 1 part in 100,000. It is the most perfect blackbody spectrum ever observed in nature, a thermal fingerprint of the infant universe. Those tiny fluctuations are hugely important. They are the seeds of all cosmic structure, the spots that would later grow into galaxies and clusters. But for our story, the most crucial feature of the CMB is its near-perfect uniformity. This ancient light isn't tied to any galaxy or star. It fills all of space, emitted before any of those structures existed. It therefore provides a backdrop that is independent of all the motion happening today. And in doing so, it provides a potential answer to our problem. A candidate for a universal reference frame. If you could find an observer who sees this ancient light as perfectly uniform in all directions at temperature of exactly 273 Kelvin, no matter where they look, you would have found someone who is, in a very real sense, at rest with respect to the expanding universe as a whole. You would have found the cosmic shoreline. The question is, are we that observer? The universe's speedometer, the CMB dipole. If we were truly at rest relative to the cosmic microwave background, we'd measure it as perfectly isotropic, the same temperature in all directions. But when astronomers pointed their sensitive instruments at the sky, starting with the COBE satellite and refined by WMAP and Planck, they found something else. While the CMB is incredibly uniform, there is one very prominent, large-scale pattern. On one side of the sky, toward the constellation Leo, the CMB is ever so slightly hotter than average. On the exact opposite side, toward Aquarius, it's ever so slightly cooler. The temperature difference is minuscule, only about 3 millikelvin, but it's unmistakable. This pattern is known as the CMB dipole. What could cause this? The answer is something we all know: the Doppler effect. When an ambulance races towards you, its siren sounds higher pitched. As it races away, the pitch drops. The same principle applies to light. Light from an object moving toward you is compressed to shorter, bluer wavelengths, a blue shift. Light from an object moving away is stretched to longer, redder wavelengths, a red shift. The CMB dipole is the ultimate cosmological Doppler effect. The hotter side of the sky isn't actually hotter. It's blue shifted. We are moving towards that direction, compressing the ancient microwave photons and giving them a bit more energy, which our telescopes see as a slightly higher temperature. The cooler side is redshifted. We're moving away from that direction, stretching the photons and causing them to lose a bit of energy. This dipole is, therefore, a direct measurement of our motion through the universe, relative to the CMB rest frame. It's the universe's speedometer. The hot and cold spots are a giant arrow painted across the sky, telling us exactly where we're going and how fast we're getting there. And the speed is staggering. After carefully calculating our motion, scientists have clocked the speed of our solar system relative to the rest frame of the universe. The number is approximately 370 kilometers per second. That's over 1.3 million kilometers per hour. Let that sink in. We can measure a single net velocity for our entire solar system as it plows through the sea of cosmic photons. This 370 kilometers per second is our peculiar velocity. It's our motion asterisk on top of the universe's general expansion. It's the sum of all the local gravitational tugs and pulls. The Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at around 220 kilometers per second. But that's not all. Our entire Milky Way galaxy, along with Andromeda and our local group, is being pulled toward a massive concentration of mass called the Great Attractor, and an even larger structure beyond that, the Shapley supercluster. When you add up all these motions, you get a net velocity for our solar system of about 370 kilometers per second toward Leo. This is our grand cosmic trajectory, beautifully revealed by the faint afterglow of the Big Bang. For cosmologists, this was an incredible breakthrough. Here was a concrete, measurable frame of reference, provided by the universe itself. It's a cosmic zero point for motion. By using the CMB as a fixed backdrop, astronomers can better map out the invisible rivers of dark matter that shape the universe. But this triumph came with a deep unease. Because in discovering this cosmic speedometer, it seemed cosmologists had stumbled upon exactly what Einstein's principle of relativity said shouldn't exist: a preferred frame of reference. The glitch in reality. A preferred frame. The discovery of the CMB rest frame created a subtle but profound tension. On one hand, Einstein's special relativity says all inertial frames are created equal. The laws of physics must be identical for an observer at rest and an observer in constant motion. You can't do an experiment to detect your absolute motion because the concept is meaningless. On the other hand, the CMB provides a frame that feels undeniably special. It's the unique frame where the Big Bang's afterglow is perfectly uniform. An observer in this frame would see no dipole, just a smooth 273 Kelvin glow. It looks, for all the world, like the universe's own private rest frame. So, which is it? Is Einstein wrong? Or are we misunderstanding something about the CMB? Let's be clear. This doesn't immediately break Einstein's relativity. The crucial part of his principle is that there are no special frames where the asterisk laws of physics themselves are different. And as far as we can tell, they aren't. An experiment in a lab moving at 370 kilometers per second gives the same results as one at rest in the CMB frame. So, in a strict sense, relativity holds. The laws are the same for everyone. Most physicists adopt a pragmatic view. The CMB frame isn't truly absolute. It is, however, a very convenient and practical frame. It's often called the co-moving frame, the one that's moving along with the average flow of cosmic expansion. Think of it like a river. The laws of physics are the same whether you're floating with the current or paddling against it. But being at rest relative to the water is a useful, natural state to describe. The CMB is the water of the cosmic river. So, the CMB rest frame isn't a crisis that brings down modern physics. Einstein can breathe a sigh of relief. It's a special frame, but not in a way that breaks his core principles. It's a glitch, a curiosity, a spooky feature of our cosmos that we happen to have this universal reference point. A preferred frame, but not a privileged one. This was the comfortable consensus for decades. A beautiful piece of cosmic architecture. The story could have ended there. But then, astronomers started looking at the universe in a different way, using different cosmic lighthouses. And they found something that didn't fit. Something that took this subtle tension and amplified it into a blaring alarm. The plot thickens, conflicting evidence. The CMB tells a clear story. We're moving at 370 kilometers per second. This measurement rests on a pillar of modern cosmology known as the cosmological principle, which says that, on the largest scales, the universe is the same everywhere and in every direction. If that's true, the CMB dipole must be caused only by our motion. But how do you test that? Decades ago, cosmologists realized that if our motion is the asterisk-only thing creating this lopsidedness, then that same motion should create a similar pattern in the distribution of anything distant. As we move through the cosmos, we should see distant galaxies and quasars looking a bit more bunched up in our direction of motion and a bit more spread out behind us, like rain appearing to come from the front when you run through it. For a long time, we didn't have maps of the sky big enough to run this test. But in recent years, massive sky surveys have finally given us the data. Surveys like the NVSS and WISE have mapped millions of distant radio galaxies and quasars across the entire sky. When scientists analyzed these catalogs, they found it. A dipole pattern in the distribution of galaxies, pointing in roughly the same direction as the CMB dipole. A good sign. But then came the shock. The size of this new, matter dipole was completely wrong. It was far, far larger than predicted. While the CMB dipole implies a speed of 370 kilometers per second, the dipole measured from these distant galaxies suggests a speed 2, 3, or even 4 times faster, closer to 500 kilometers per second. This is the cosmic dipole anomaly, and it's one of the most perplexing tensions in modern cosmology. We have two cosmic speedometers, and they're giving us wildly different readings. The speedometer based on ancient light gives one number. The speedometer based on distant matter gives another, much higher number. This discrepancy has now reached a statistical significance of over 5 sigma in some analyses. In particle physics, that's the gold standard for a discovery. It means there's less than a 1 in 5 million chance the result is a random fluke. This anomaly appears to be real. Scientists have scrambled to figure out what's going on. Could there be an error in the galaxy surveys? Researchers have been meticulously checking, but the anomaly has persisted. As the data gets better, the discrepancy hasn't gone away. If anything, it's become sharper. If the measurements are correct, we're faced with some radical possibilities. One is that the cosmological principle is wrong. The universe, on the largest scales, might not be the same in all directions. There could be a preferred direction, a tilt, or a flow in the cosmic web, built into the very fabric of space. Another, even more mind-bending possibility is that the rest frame of matter is simply not the same as the rest frame of radiation. That would mean the water of the cosmic river, the CMB, is flowing in one direction, while the stuff in it, the galaxies, is flowing, on average, in another. This would shatter our simple picture of a uniformly expanding cosmos, suggesting our standard model of cosmology is missing a fundamental piece. This isn't a settled debate. It's a live, unfolding mystery. The cosmic dipole anomaly is a direct challenge to the foundations of our standard model. So what do you think is going on? Are we seeing the first cracks in our most fundamental theories? Is the idea of a uniform cosmos about to be overturned? Or is this all just a subtle error in our measurements we haven't found yet? Let me know your theories down in the comments. And if you find your mind stretched by these kinds of cosmic puzzles, make sure you subscribe, because we're just getting started. Reconciling Einstein and the CMB. Faced with this growing anomaly, where do we go? The first instinct is to re-examine the assumptions. The most conservative explanation is that we're still being fooled by something more mundane than a breakdown of fundamental physics. The universe is messy. The space between us and distant quasars is filled with dust, and our own galaxy's light is a brilliant foreground that must be perfectly subtracted. Indeed, some of the very latest analyses hint that when we combine multiple different surveys, the results can get a little closer to what the CMB predicts, though the uncertainties are still large. This offers a path back to consistency, suggesting that as our surveys get even better, the anomaly might simply melt away. But what if it doesn't? What if the anomaly is real? How do we reconcile this with over a century of physics? Even in the face of this tension, the mainstream view is that the CMB rest frame is not a true violation of relativity. The principle that the asterisk laws of physics are the same in all inertial frames remains unshaken. The CMB frame is special simply because it's where the universe's baby picture looks the simplest. It's an artifact of our cosmic history, not a feature of fundamental law. However, the dipole anomaly forces us to question the asterisk other pillar. The cosmological principle. Our standard model of cosmology is built on a mathematical framework that assumes a perfectly homogeneous and isotropic universe. It's this simplification that lets us solve Einstein's incredibly complex equations. But what if this assumption is only an approximation? The dipole anomaly might be our first clear sign that the universe is not perfectly uniform. There could be an inherent anisotropy, a preferred direction, baked into the cosmos from the start. This doesn't mean Einstein is wrong, but that our application of his theory has been too simple. More complex models that allow for a tilted universe could naturally produce a scenario where the matter and radiation frames don't align, creating exactly the kind of discrepancy we see. This would be a revolution. It would mean our universe is lopsided. Many of our cosmological calculations would have to be re-evaluated. Estimates for things like dark matter and dark energy might need to be revised. It would fundamentally change our map of the cosmos. This anomaly is part of a growing set of tensions in cosmology. You may have heard of the Hubble tension, another major discrepancy in measuring the universe's expansion rate. Some researchers wonder if these are all pointing to the same conclusion. Our standard model, while incredibly successful, is incomplete. The cosmic dipole anomaly is arguably the most fundamental of these challenges because it questions the very symmetry of the stage on which all the cosmic action plays out. It's not just about how fast things are happening, but about the nature of the space they are happening in. So, the glitch remains. For now, it hasn't broken Einstein's theory, but it has put a serious dent in the cosmological principle. We are in a state of fascinating uncertainty. We have this ancient signal that provides a cosmic rest frame, an anchor in the expanding sea of galaxies. But we also have mounting evidence that this anchor might not be as simple as we thought, and our maps of the cosmic ocean may need to be redrawn. We started with a simple question, born from Einstein's revolution. In a universe where everything is moving, what does it mean to be still? For decades, the answer was that the question itself was meaningless. There is no absolute rest. Then, we found it. A ghost from the past. The cosmic microwave background, the faint afterglow of creation, provided us with a universal backdrop, a cosmic rest frame to clock our speed through the void. We measured our motion with stunning precision, 370 kilometers per second. It was a triumph, a beautiful confirmation of our cosmic model. It seemed that while Einstein was right in principle, the universe had handed us a convenient, practical exception. But the universe rarely gives simple answers. The story took a sharp turn. When we tried to cross-check this velocity against the matter of the universe itself against millions of distant galaxies, the numbers didn't add up. The speedometer of matter gave a different reading from the speedometer of light, a discrepancy that has grown into a 5 sigma crisis for cosmology. A cosmic dipole anomaly that suggests a fundamental mismatch between our model of the universe and the universe itself. This is where we are now, living inside the paradox. We are left with a glitch in our understanding of reality. This faint echo of the Big Bang has both anchored our place in the cosmos and, simultaneously, revealed a deep crack in our map. It has challenged the cosmological principle, the very assumption of uniformity that underpins our standard model. The Big Bang didn't just leave behind a faint glow. It left behind a puzzle, a clue that points towards either a profound misunderstanding of our data or a profound truth about the lopsided, anisotropic nature of our universe. It challenges us to reconsider our most basic assumptions. Einstein's principle of relativity remains a pillar of physics, but his vision of a simple, uniform cosmos may be giving way to a stranger, more complex, and ultimately more interesting reality. The quest to understand this glitch isn't just about measuring our speed. It's about understanding the fundamental shape of our home, the universe itself. And it's a quest that is far from over. Gravity's secret war against cosmic expansion. For 13.8 billion years, a secret war has been raging. It's a conflict that will decide the fate of everything that is, was, and ever will be. This isn't a war fought with armies or empires, but one between fundamental forces, playing out on a scale so vast it's almost impossible to wrap your head around. It's a silent, invisible tug of war across the entire cosmos. On one side, you have a force you know well, gravity, the architect of worlds and sculptor of galaxies, tirelessly pulling everything together. On the other side is its mysterious opponent, The relentless expansion of space itself, a force that's been pushing everything apart since the instant of the Big Bang. The only reason you're here on this planet, in this solar system, able to even wonder about this cosmic battle is because, in our own cosmic neighborhood, gravity won a crucial victory. But on the grandest scale, the war still rages. For decades, we thought we knew who was winning. We'd discovered a mysterious phantom, a dark energy, that was tipping the scales. But just when the story seemed settled, new evidence has thrown everything into chaos. This is the story of that war, a war between the creative power of gravity and the dissipating push of expansion. It's the story of how we came to be, and how it all might end. The battlefield, an expanding universe. To get a grip on this cosmic conflict, we first have to understand the battlefield. For most of human history, we looked at the night sky and assumed it was a fixed, eternal stage. The stars were just points of light in a great, unchanging celestial sphere. This view was comforting, tidy, and, as we now know, completely wrong. The revolution kicked off in the early 20th century. Astronomers like Vesto Slipher noticed something odd about the light from distant, spiral nebulae. When he passed their light through a prism, the spectral lines of the elements inside were shifted. For almost all of them, the lines were shifted toward the red end of the spectrum. This redshift was a clue of monumental importance. In physics, redshift is the telltale sign that a light source is moving away from you, like how the pitch of an ambulance siren drops as it speeds past. Slipher had found that nearly all the galaxies he could see were rushing away from us. But it was American astronomer Edwin Hubble who, in the 1920s, put all the pieces together and shattered our view of the cosmos. Using the brand new Hooker telescope at Mount Wilson Observatory, Hubble proved two world-changing things. First, he showed that those spiral nebulae weren't gas clouds in our own Milky Way, but were immense, independent, island universes, galaxies in their own right. Second, and even more profoundly, he found a clear link between a galaxy's distance and its speed. The farther away a galaxy was, the faster it was receding from us. This discovery, now called the Hubble-Lemaitre law, was staggering. It meant the universe wasn't static, it was expanding. The best way to picture this is to imagine a loaf of raisin bread dough rising in an oven. As the dough bakes and expands, every raisin moves farther from every other raisin. From the viewpoint of any single raisin, all the others appear to be moving away. The raisins themselves aren't actually moving through the dough. The dough itself, the very space between them, is expanding. That's what's happening in our universe. It's not that galaxies are blasting through some pre-existing void. Space itself is stretching, carrying the galaxies along for the ride. This also explains why there's no center of the expansion. Every point is like every raisin. From any vantage point, everything else appears to be moving away. The Big Bang wasn't an explosion in space. It was the beginning of the expansion of space. Hubble's discovery set the stage for all of modern cosmology. It meant that if you ran the clock backward, the universe would get smaller, denser, and hotter, until you reached a moment of unimaginable density and energy, the Big Bang. And from that moment, the war began. The initial push of expansion started separating matter, while gravity, inherent in all that matter, immediately started fighting back. The first victor. Gravity's local win. The discovery of an expanding universe brings up a pretty personal question. If the whole cosmos is stretching, why aren't we? Why isn't the Earth expanding, or our solar system flying apart? Why do you stay the same size? The answer is gravity's first great victory. While cosmic expansion rules the vast, empty highways between galaxies, it's a surprisingly weak force on smaller, local streets. In these local arenas, gravity is the undisputed champ. And that's the secret to our existence. Let's go back to the raisin bread. The dough expands, but the raisins themselves don't. A raisin is a bound system. The forces holding it together are way stronger than the gentle stretching of the dough. In the cosmos, galaxies, stars, planets, and even you are the raisins. Cosmic expansion isn't a forceful push. It's more like a persistent, background hum of new spacetime being created. Its speed is described by the Hubble constant, which, despite an ongoing debate called the Hubble tension, is roughly 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So, for every 3.26 million light-years you look out, things are moving away 70 kilometers per second faster. That sounds incredibly fast, but on everyday scales, it's almost nothing. The outward pull of cosmic expansion across the diameter of the Earth is trillions of times weaker than the planet's gravity holding you to the ground. It's totally irrelevant. The gravitational bond holding you to the Earth easily overpowers it. Now let's zoom out to the solar system. The Sun's immense gravity locks the planets in stable orbits. They aren't drifting away because the Sun's gravitational grip is millions of times stronger than the tiny expansive tug across that same distance. Zoom out even further to our Milky Way galaxy. It's a gravitationally bound island of stability in the expanding cosmic ocean. All its hundreds of billions of stars are held together by the combined gravity of all that mass stars, gas, dust, and dark matter. The same goes for our immediate cosmic neighborhood, the local group. Our biggest neighbor, the Andromeda Galaxy, isn't receding. In fact, it's hurtling towards us at over 100 kilometers per second, and in about 4.5 billion years, our two galaxies are set for a spectacular merger, all thanks to gravity's local dominance. It's only when you get to scales of many millions of light-years that gravity's grip weakens enough for cosmic expansion to take over. The vast voids between galaxy clusters are where space really stretches. This is the crucial first act of our story, gravity's victory on the local level. It doesn't stop the universe from expanding, but it carves out pockets of stability. It creates islands where matter can gather, build structures, and give life a chance. Without this local win, we wouldn't be here. The architects of everything. How gravity built our world. Gravity isn't just a defender in this cosmic war. It's a creator. It's the grand architect that took the raw material of the early universe and sculpted the complex structures we see today. Its local victory was the start of creation itself. Let's rewind to about 380,000 years after the Big Bang. Before this, the universe was a scorching, opaque fog of particles and radiation. But as the universe expanded, it cooled. At about 3,000 Kelvin, a critical event happened. Recombination. Protons and electrons finally paired up to form neutral hydrogen atoms. Suddenly, light was free to travel across the cosmos, and the universe became transparent. That primordial light is what we now see as the cosmic microwave background, CMB, a faint afterglow of creation filling the entire sky. The CMB shows us that the early universe wasn't perfectly smooth. There were tiny density fluctuations, regions just a fraction of a percent denser than their surroundings. These tiny seeds were all gravity needed. Gravity amplifies differences. A slightly denser region has a slightly stronger gravitational pull. Over millions of years, it draws in more matter, growing richer as the surrounding areas grow poorer. This is how the cosmic web was born, a vast, intricate network of filaments and clusters of galaxies, separated by immense voids. The invisible scaffolding for this was dark matter, which doesn't interact with light and had already started clumping together even before recombination. Ordinary matter was then drawn into these pre-existing dark matter halos. Inside the densest knots of this web, gas clouds kept collapsing. Their cores grew hotter and denser until, after a few 100 million years, a new fire was lit: nuclear fusion. The first stars were born, ending the cosmic dark ages. These first-generation stars were giants. They lived fast and died young in brilliant supernovae, seeding the cosmos with the first heavy elements: carbon, oxygen, iron forged in their hearts. These are the elements that make up planets and life itself. From there, gravity's work continued. Those first stars and their remnants formed protogalaxies, which merged and collided over billions of years to create the grand galaxies we see today. Inside those galaxies, new generations of stars were born, including our own sun. And around that sun, gravity patiently gathered dust and rock to form the planets, including one where it held an atmosphere and liquid water, creating the perfect conditions for life to emerge. Every star, every planet, every living thing is a monument to gravity's creative power. The plot twist. A hidden enemy. For most of the 20th century, the story seemed simple. The universe was expanding, but the gravity from all the matter within it must be acting as a cosmic brake, slowing things down. The big question was whether there was enough gravity to stop the expansion and reverse it into a big crunch, or if the universe would expand forever in a big freeze. Then, in 1998, everything changed. Two teams of astronomers were using a special kind of exploding star, a Type Ia supernova, as a standard candle, to measure how much the expansion had slowed over time. They expected to find that distant supernovae were brighter than they should be, a sign that the universe was expanding faster in the past. But they found the exact opposite. The distant supernovae were dimmer than expected. They were farther away than they should be. The only way to explain this was if the expansion of the universe had stopped slowing down and had started to accelerate. This discovery, which won the 2011 Nobel Prize, was a shock. It was like throwing a ball in the air, only to see it suddenly shoot upwards, faster and faster. The cosmic brakes weren't just failing. Someone had slammed on a cosmic accelerator. This implied a new player in the game: dark energy. This mysterious entity seems to be a property of spacetime itself, acting like a form of anti-gravity that pushes the universe apart. For the first 9 billion years, gravity was winning and the expansion was slowing. But as matter spread out, gravity's influence weakened. About 5 to 6 billion years ago, a tipping point was reached. The repulsive push of dark energy became dominant, and the universe's acceleration began. For over 2 decades, this was our new story. But just when we thought we had it figured out, the plot twisted again. Recent studies, particularly from a team at Yonsei University, have delivered another bombshell. By re-examining those same Type Ia supernovae, they found a subtle but crucial bias. The brightness of these explosions seems to depend on the age of their parent stars. After correcting for this age bias, the picture changes dramatically. The evidence for acceleration vanishes. In fact, the data now suggest the universe's expansion is no longer accelerating, it's decelerating. The hidden enemy we thought we'd unmasked might be weakening, and the entire war could be about to change course once more. The Three Fates, a cosmic trilemma. The discovery of dark energy's acceleration introduced a dramatic set of possible endings for our universe. But the latest revelations that this acceleration may now be a deceleration have reshuffled the odds, making the ultimate outcome more uncertain than ever. Here are the 3 leading scenarios for how this cosmic war could end. Scenario 1. The Big Crunch, gravity's final revenge. This is the ending that was mostly dismissed for 25 years but has now made a stunning comeback. In a big crunch, gravity gets the last laugh. This happens if dark energy is a temporary phenomenon that weakens over time, allowing gravity's pull to eventually halt and reverse the expansion. The recent studies suggesting that dark energy is evolving and that the expansion is now decelerating make this a serious possibility again. If this trend continues, the universe would experience the Big Bang and rewind. Galaxies would stop flying apart and start rushing toward each other. The cosmos would grow hotter and denser. Billions of years into the contraction, galaxies would merge, and stars would be cooked from the outside in before vaporizing. In the final, frantic moments, atoms themselves would be ripped apart, and everything would be crushed back into an infinitely hot, dense singularity. Some physicists speculate this could trigger a big bounce, a new Big Bang creating a new universe. Scenario 2. The Big Freeze, a cold and lonely end. This was, until very recently, the most favored scenario. It's the future we expect if dark energy is an unchanging, cosmological constant. In this version, cosmic expansion wins, and the universe expands forever at an ever-accelerating rate. From our galaxy, we'd watch as all other galaxy clusters speed away until their light could no longer reach us, vanishing one by one into a black, empty sky. Our own merged galaxy, Milky Way, would remain as an isolated island. But even here, time would take its toll. The gas for new stars would run out. Over trillions of years, all existing stars would die, leaving behind a dark cosmos of cold remnants like black holes and white dwarfs. Over unimaginable timescales, even these would decay. The final result would be a vast, dark, and empty universe near absolute zero, where all structure is gone and time itself becomes meaningless. It's a quiet, solemn fade to black. Scenario 3. The Big Rip, a violent conclusion. The third and most terrifying fate is the Big Rip. This would happen if dark energy is a hypothetical, superpowered version called phantom energy, whose repulsive force grows stronger over time. If this is our destiny, the end would be cosmically swift and brutal. The accelerating expansion would become so strong it would first tear apart galaxy clusters. Then, individual galaxies like our own Milky Way would be unwound. As the end neared, the expansion would overpower the gravity holding solar systems together, flinging planets into the void. In the final minutes, Earth itself would explode. In the last fraction of a second, the expansion would become so ferocious it would overcome the forces holding atoms together, and finally, even atomic nuclei would be torn asunder. Spacetime itself would be ripped apart in a final, all-encompassing shredding of reality. The current score. Who is winning? So, where do we stand today? Who's winning this cosmic war? For about 25 years, the answer seemed clear. Dark energy was dominant, and we were heading for a big freeze. But now, the game has changed completely. The story of acceleration was built on three pillars. Type Ia supernovae, the cosmic microwave background, CMB, and maps of the universe's large-scale structure, LSS. For years, all three seemed to support the lambda CDM model, our standard model of cosmology, where lambda represents a constant dark energy making up about 70% of the universe. But that foundation is now shaking. The new research from Yonsei University, published in the * monthly notices of the Royal Astronomical Society, argues that after correcting for the age bias in supernova data, the evidence for current acceleration disappears. When they combine this corrected data with other cosmic probes like baryonic acoustic oscillations, BAO, from LSS surveys, they find a strong disagreement with the standard lambda CDM model. Their analysis indicates that dark energy is evolving and weakening, and the universe has already started to decelerate. This has turned what was once a fringe idea into a mainstream challenge to our understanding of the cosmos. Meanwhile, the Hubble tension, a persistent disagreement between measurements of the expansion rate today versus in the early universe, continues to puzzle physicists. New methods, like using the stochastic siren, of gravitational waves from colliding black holes are being developed to get an independent measurement, but they have not yet resolved the tension. What does this all mean? It means the final chapter is not yet written. The idea that gravity was losing the ultimate war is now in serious doubt. The Lambda CDM model, for all its success, is facing its biggest challenge yet. The scientific consensus is shifting from a settled conclusion to a state of thrilling uncertainty. Gravity might be making a comeback on the cosmic scale, and the ultimate fate of the universe is once again up for grabs. This cosmic battle, with its shocking twists, is one of the most profound stories in all of science. With the universe's fate suddenly uncertain again, which ending are you rooting for? The fiery rebirth of a big crunch, the quiet eternity of a big freeze, or the violent end of a big rip? Let us know your thoughts in the comments below. And if you enjoy exploring the biggest questions about our cosmos, please consider liking this video and subscribing for more journeys to the frontiers of science. Our journey through this 13.8 billion-year war reveals a universe far more dynamic and mysterious than we ever imagined. We've seen how gravity, in a constant tug of war with the expansion of spacetime, acted as both a defender and a creator. It carved out a gravitational sanctuary where stars, planets, and life itself could form. We exist because gravity won the local battles. But looking out to the grandest scales, the story took a shocking turn. The discovery of dark energy in 1998 suggested a powerful new adversary was pushing the universe towards an accelerated, lonely end. For a generation, it seemed gravity was losing the war. But science is a story that's constantly being revised. The latest evidence suggests the tide may be turning. Puzzles like the Hubble tension and new analyses of supernovae challenge our standard model and breathe new life into the idea that gravity's influence may once again come to dominate. We live in a remarkable time, able to piece together the cosmic story from its first moments to its possible ends. We find ourselves in a universe shaped by a delicate and shifting balance between the pull of gravity and the push of dark energy. The fact that the final chapter remains unwritten is not a failure of science, but its greatest thrill. The secret war rages on, and as we keep gazing into the darkness, we are reminded that the universe's greatest secrets may still be waiting to be discovered. The biggest lie about the universe you still believe. You've seen it 100 times. In movies, in documentaries, on the posters in your middle school science class. A single, brilliant point of light hanging in an infinite black void. And then, bam! A universe erupts. Galaxies fly outwards like shrapnel from a cosmic bomb, populating a vast, pre-existing emptiness. This is the Big Bang, right? The story of creation we've all been told. Well, that's the biggest lie about the universe you still believe. The story isn't just a little bit wrong. It's wrong in a way that completely warps our understanding of reality, our place in the cosmos, and the very nature of space and time. The Big Bang wasn't an explosion in space. It was the expansion of space itself, happening everywhere, all at once. There was no single point. There was no empty void for it to explode into. And the most mind-bending part? It means there is no center of the universe. No special place, no grand origin point, no cosmic X that marks the spot. So, get ready to have your mind re-centered. In this video, we're going to dismantle the biggest misconception in cosmology. We'll journey back to the first moments of existence, not to find a center, but to understand why one doesn't exist. And in doing so, we'll discover what that really means for who we are, and where we are, in this boundless, centerless reality. This isn't just about correcting a science fact, it's about changing how you see everything. Deconstructing the explosion. So, where did we even get this idea of a cosmic bomb? Honestly, it's completely understandable. The name itself, the Big Bang, paints a picture of a violent, cataclysmic explosion. It's catchy, but it's also one of the most misleading terms in all of science. Ironically, it was coined by someone who hated the whole concept. Back in 1949, astronomer Fred Hoyle was a big believer in the steady-state theory, which said the universe was eternal and basically unchanging. He used the phrase, Big Bang, on a BBC radio program to mock the competing idea, this new, ridiculous theory that the universe actually had a beginning. He meant for it to sound silly, like a sound effect from a comic book. But the name stuck. And with it, a powerful and deeply flawed image got stuck in our collective heads. Pop culture grabbed it and ran. We see it everywhere. A bright flash in the darkness. It's an easy visual and a simple story. Our brains are wired for that kind of cause and effect. A bomb has a center. When it goes off, stuff flies outwards into the surrounding air. We can stand back and point to the epicenter. That's how explosions work in our world. But the Big Bang was nothing like that. To get why, we have to toss out our most basic instinct, the idea of a pre-existing stage. With a bomb, the stage, the space, the air, the ground is already there. The explosion is just an event that happens within that stage. The Big Bang wasn't an event in space. The Big Bang was the event that created space. There was no outside for it to expand into. There was no around it. There was no empty void waiting to be filled. Asking what the universe expanded into is like asking what's north of the North Pole. The question itself doesn't make sense. Think of it this way. Imagine you could rewind time all the way back to the first sliver of a second. As you got closer to the beginning, you wouldn't be zooming in on a tiny dot in a black void. Instead, you'd see all of space shrinking. Everything would get closer to everything else. The distance between where our Milky Way would one day be and where the Andromeda Galaxy would one day be would shrink. All points in the cosmos would collapse, not toward a center, but toward each other. The Big Bang didn't happen at a single point. It happened everywhere. The spot you're in right now? The Big Bang happened there. The location of the most distant galaxy we can see? The Big Bang happened there, too. 8 billion years ago, every single point in our observable universe was in an unimaginably hot, dense state. The bang was the moment the fabric of space itself began to expand, everywhere, at the same time. This is a subtle but massive difference. It takes us from a simple, wrong picture of a cosmic firework to a much stranger, truer picture of an entire reality unfurling. To really get this, we need to upgrade our mental toolkit from explosions to the mind-bending world of modern physics and a very famous, stretchy analogy. The heart of the matter, the expansion of spacetime. To truly ditch the explosion lie, we have to embrace one of the most powerful ideas ever conceived, Albert Einstein's theory of general relativity. Before Einstein, we saw space as a fixed, empty box, a boring backdrop for the action. But Einstein showed us that space isn't separate from time. They're woven together into a dynamic fabric called spacetime. And this fabric isn't just a passive stage. It has properties. It can bend, it can warp, and, most importantly for our story, it can stretch. What we call gravity is just the curvature of spacetime caused by mass and energy. A star doesn't pull a planet into orbit. The star makes a big dimple in the spacetime fabric, and the planet is just rolling along the curved edge of that dimple. Once you accept that space is a thing that can be acted on, the Big Bang starts to make a lot more sense. It wasn't matter flying through static space. It was the fabric of spacetime itself unfurling. It was an expansion of space, not in space. This is where the go-to analogy for every cosmologist comes in handy. The balloon. Imagine you have a deflated balloon. Take a marker and draw a bunch of dots on its surface. Each dot is a galaxy. Now, start blowing up the balloon. What happens? As the rubber stretches, every dot moves away from every other dot. From the perspective of any one dot, it looks like all the other dots are running away from it. A nearby dot moves away slowly. A dot on the far side of the balloon races away. This is a perfect mirror of what we see in the real universe. Galaxies are moving away from us, and the farther away they are, the faster they appear to go. Now for the million-dollar question. Where's the center of the expansion? Think about it. Is there a center dot that all the others are fleeing from? Nope. The expansion is happening on the 2D surface of the balloon itself. For a little two-dimensional creature living on that surface, there is no center to point to. An ant on any one of those dots would look around and declare, "I am the center of the universe. Everything is moving away from me." And from its perspective, it would be right. But so would an ant on any other dot. The actual center of the balloon, that point in the middle of the air inside, isn't part of their 2D universe. It exists in a third dimension they can't see or touch. In the same way, our three-dimensional universe might be expanding from a center in some hypothetical fourth spatial dimension, but within our 3D space, no center exists. The expansion is just a property of the space itself. Of course, the analogy isn't perfect. The balloon is 2D, our universe is 3D. And the balloon is expanding into the 3D space of the room. As we've covered, our universe isn't expanding into anything. But the key takeaway is that you can have expansion where every point moves away from every other point without a central starting position. To hammer this home, let's try one more. A loaf of raisin bread dough. The dough is space-time and the raisins are galaxies. As the dough bakes and rises, it expands everywhere. Every raisin moves away from every other raisin. A raisin in the middle sees its neighbors move away, but a raisin near the edge sees the exact same thing. No raisin is special. The expansion is happening in the dough itself. Crucially, both analogies clarify that the galaxies themselves aren't expanding. The marker dots don't grow. The raisins don't get puffy. Gravity is strong enough on local scales to hold galaxies and star systems together against the cosmic tide. Our Milky Way isn't expanding. You're not expanding. It's the vast, gravitationally unbound space between galaxy clusters that's stretching. This is a monumental shift in thinking. The universe isn't a bunch of objects moving through a void. It's a dynamic, stretching fabric of spacetime, and we're all just along for the ride. With this new picture in mind, we can finally look at the evidence that's been staring back at us all along. Evidence for a center-less universe. This whole idea of a center-less, expanding universe isn't just a clever thought experiment. It's one of the most rigorously tested truths in science, backed up by solid, independent evidence. The first clue came in the 1920s from astronomer Edwin Hubble. He made the stunning discovery that almost every distant galaxy is moving away from us. Even more shocking, he found a clear pattern. The farther away a galaxy is, the faster it's moving away. This became known as Hubble's law. At first glance, this seems like proof that we are the center. If everyone in a crowd runs away from you, it feels pretty special. For a moment, it looked like we had a privileged seat in the cosmos. But science has a principle for this, called the Copernican principle. It basically says we're probably not special. We're not the center of the solar system, our sun is an average star, and our galaxy is one of billions. So, if we see all galaxies moving away from us, science assumes that an observer in any other galaxy must see the exact same thing. And how is that possible? Go back to the balloon. From any dot, all the other dots are receding. Hubble's law works for every single dot. What Hubble found wasn't proof of our specialness. It was the first proof that space itself was expanding. We appear to be at the center, but so does everybody else. But the absolute smoking gun for a Big Bang that happened everywhere is a faint glow that fills the entire sky. The cosmic microwave background, or CMB. For the first 380,000 years, the universe was an opaque, scorching hot plasma fog. Light couldn't travel anywhere without bouncing off a particle. But as the universe expanded, it cooled. Eventually, it cooled enough for the fog to clear, and all that trapped light was set free. The cosmic microwave background is that ancient light, the afterglow of creation. As the universe has continued to expand for 13.8 billion years, this light has been stretched out. What started as brilliant, hot light is now, after all that time, a cold wash of microwaves with a temperature of just 725 degrees above absolute zero. When astronomers first detected this radiation in 1964, they found it was coming from every single direction, with almost the exact same temperature. The variations are minuscule, about 1 part in 100,000. Now, think about the old bomb model. If the Big Bang was a single explosion, we'd expect to see a hot spot in the sky in one direction, the blast wall, and cold emptiness in the other. We don't. We see the afterglow in every direction. This is the ultimate proof. We are, in a very real sense, still inside the cooled-down embers of the Big Bang. And there's more. The Big Bang model also predicted a faint background of neutrinos that would have been released even earlier than the CMB, just 1 second after the beginning. For decades, this cosmic neutrino background was purely theoretical. But in recent years, by studying subtle patterns in the CMB and the distribution of galaxies, scientists have found strong indirect evidence of these relic neutrinos, perfectly matching the predictions. The mind-bending consequences. Once you accept that space itself is stretching, reality starts to get even weirder. First, there's the universe's ultimate speed limit, the speed of light. Einstein's theories are clear. Nothing can travel through space faster than light. So how can some galaxies be moving away from us faster than that? Remember the key distinction. Objects moving through space versus space itself expanding. The speed of light is a local traffic law. But there's no speed limit on the expansion of space itself. Go back to the balloon. An ant crawling on the surface has a top speed. But if you inflate the balloon fast enough, 2 dots on opposite sides can move away from each other much faster than the ant can crawl. It's the rubber between them that's doing the work. This is exactly what's happening. Because of cosmic expansion, there's a point, the Hubble horizon, beyond which galaxies are receding from us faster than the speed of light. The light they are emitting right now will never reach us. The space between us and them is expanding so fast that the light is like a swimmer fighting a current that's just too strong. This leads to the difference between the observable universe and the entire universe. The observable universe is just a bubble around us, about 46.5 billion light-years in radius. That's not a physical edge. It's just the horizon beyond which light hasn't had time to reach us in 13.8 billion years. What lies beyond that? It could be incomprehensibly vast, maybe even infinite. We'll simply never know. So what's driving all this expansion? For a long time, cosmologists thought gravity would be putting the brakes on everything. But in the late 1990s, they found the exact opposite. The expansion is speeding up. To explain this, physicists proposed a mysterious force called dark energy. And for decades, the leading idea was that it was a cosmological constant, a constant, repulsive property of space itself. As more space gets created, more dark energy appears, pushing space to expand even faster. But the story might be taking another wild turn. Recent data from major projects like the Dark Energy Survey, DE, and Dark Energy Spectroscopic Instrument, DESI, have hinted that dark energy might not be constant after all. Some of this 2026 data suggests it might be evolving or changing over time. If these hints hold up, it could mean the fate of the universe isn't a runaway expansion into a cold, dark, big freeze. Some models based on this new data suggest the universe could be heading for a dramatic reversal, with the expansion slowing, stopping, and ultimately collapsing back in on itself in a big crunch, some 20 billion years from now. Lingering questions on the edge of knowledge. This new picture of the cosmos, a centerless, edgeless, possibly evolving expanse, is humbling. It also forces us to face what we don't know, which is just as important as what we do. The question, what is the universe expanding into, still comes up. But as we've seen, it's based on a faulty premise. If the universe is all of spacetime, there is no into. A better question is, what happened before the Big Bang? Here, our current laws of physics just break down. Time itself seems to begin at that moment, making the word before meaningless. This is the realm of pure speculation, but it's where science pushes forward. And there are mysteries we can investigate right now. One of the biggest puzzles in cosmology is the Hubble tension. Simply put, when we measure the expansion rate of the universe today using nearby objects, we get one number. But when we use our model of the early universe and the CMB to predict what the rate should be today, we get a different, slower number. The numbers don't match, and the discrepancy is too big to be a simple error. This tension is thrilling for physicists. It could be a sign that our standard model of cosmology is missing something big. And this is where the next revolution might come from: gravitational waves. These ripples in spacetime, first detected in 2015, give us a completely new way to see the universe. By observing the gravitational waves from colliding neutron stars, events called standard sirens, we can measure cosmic distances in a totally independent way. Recently, scientists have even proposed using the faint, continuous hum of countless black hole mergers across the cosmos to make this measurement even more precise. This new method might just be the tiebreaker needed to solve the Hubble tension and tell us if we're on the verge of discovering brand new physics. If this journey to the edge of cosmic understanding has shattered your old perspective, only to rebuild it with something far more wondrous, then you're in the right place. We love dismantling simple lies to reveal deeper, stranger truths. So hit that subscribe button, because the universe is more bizarre and beautiful than we can imagine, and our exploration is just getting started. So, we're back where we began, but with new eyes. The image of a cosmic bomb is gone, replaced by a far more majestic and bizarre reality. The Big Bang was not an explosion in space, it was the start of the expansion of space itself, happening everywhere. For 13.8 billion years, that fabric has been stretching, cooling, and evolving, carrying us along with it. We are adrift in a cosmos with no center to point to and no edge to fall from. Every shred of evidence, from the light of distant galaxies to the omnipresent afterglow of creation, confirms this incredible story. This truth doesn't demote us. It liberates us. The old view, with a special center, was a story of privilege. The true story is one of profound unity. The very spot you occupy right now was there at the dawn of time. The atoms in your body were forged in stars that are just temporary eddies in this vast, expanding sea. You are not a spectator watching the universe from a special seat. You are a piece of the universe, observing itself. There is no center. Or maybe, it's better to say that everywhere is the center. You are, from your own unique perspective, at the center of your own observable universe. And that is a profound and beautiful thought. The universe doesn't revolve around you, but the story of the universe, as you can see it, absolutely does. And that is no lie. The universe's missing anchor and our great illusion. Go on, look around you. The room you're in, the chair you're on, the ground beneath your feet. It all feels solid, stable, fixed. It feels like the one firm thing you can count on in a universe that's always changing. But what if I told you that feeling is a lie? A deep and universal illusion. What if the ground, the Earth, our entire galaxy is hurtling through the cosmos at speeds you can't even imagine, with no fixed point to call home, and no, still, to be still against? It turns out the very idea of standing still is a fantasy our brains made up to cope with a reality that is far, far stranger than we think. So for the next few minutes, we're going on a journey to tear down that illusion. We're going to peel back the layers of motion, one by one, until you feel the dizzying truth of your own cosmic speed. And when we do, we won't just be learning about physics. We'll be finding a new, more profound truth about our place in the cosmos. Not that we're lost in space, but that we are part of its magnificent, dynamic, and groundless dance. Right now, you are moving at over 1,000,000 miles per hour, and yet, you feel perfectly still. There's no rush of wind, no G-forces pressing you into your seat. Nothing. This feeling, this deep, instinctual sense of stability, is maybe the greatest illusion in the universe. And the truth it's hiding is stranger and more beautiful than a simple, stationary Earth. The truth is, there's no still to begin with. There's no such thing as absolute rest. Everything, and I mean everything, is in motion, all the time. Our hunt for a fixed point, for some ultimate anchor, is a ghost hunt. The universe simply doesn't have one. And understanding why changes everything. The anchor we invent, our everyday illusion. Our journey doesn't start in a spaceship, but on a train. Imagine you're on a perfectly smooth train, gliding along a straight track at a constant speed. The windows are blacked out. No bumps, no vibrations, no sounds. You toss a ball straight up into the air. What happens? It comes right back down into your hand. You pour a cup of coffee, and it fills the cup just like it would in your kitchen. You walk down the aisle, and your steps feel totally normal. Now, if I asked you, are you moving? What would you say? Based on every clue you have inside that train car, the only logical answer is no. From your perspective, you're at rest. But this isn't just a quirky thought experiment. It's a deep principle about reality that Galileo first grasped centuries ago. He imagined a sailor below the deck of a smoothly sailing ship and realized there's no experiment you can do without looking outside to tell if the ship is moving or standing still. The laws of physics are the same in both cases. This is what physicists call an inertial frame of reference, basically, any place moving at a constant velocity, where physics behaves as you'd expect. Our brains, though, aren't built for this. We are creatures of the Earth. For our entire evolutionary history, the ground has been the ultimate, non-negotiable reference point. It is still. We instinctively divide the world into the thing that is moving and the thing that is not. The train moves. The ground doesn't. But what happens when you open the blinds on that train? Suddenly, the world is rushing past. Now you know you're moving. But what really changed inside the train? Nothing. The ball still falls straight. The coffee still pours perfectly. The only thing that changed was you got a new frame of reference. The world outside. Your brain instantly decides the ground is the true, stationary frame and concludes, I'm moving at 100 miles per hour. But is that the only right answer? An observer on the platform agrees. But what about a passenger on another train, on a parallel track, moving at your exact same speed? Looking over, they'd see you as perfectly still. So who's right? The person on the platform who says you're flying by, or the passenger on the other train who says you're not moving at all? The profound answer, the one that kicks off our entire cosmic journey, is that they're both right. Motion isn't a property an object has. It's a relationship between objects. This is the principle of relativity, and it's the first crack in the foundation of our common sense. There is no absolute speed. There is no universal speedometer. And as we're about to see, when we look for an ultimate reference point for the entire universe, we find there isn't one. The ground, the very Earth itself. It's all just another train car in motion. Losing our anchors. The cosmic vertigo. Okay, so motion is relative. On Earth, we use the ground as our handy, if not truly, absolute, anchor. But now, let's start pulling the camera back. Let's start kicking away these anchors, one by one. Prepare for some cosmic vertigo. First anchor. The ground. You feel stationary, but you're on a spinning planet. If you're standing at the equator, you're whipping around the Earth's axis at about 1,040 miles per hour, or roughly 1,670 kilometers per hour. That's faster than the speed of sound. You don't feel it because you, the atmosphere, and everything around you are all moving together just like a passenger on that smooth train. Next anchor to go. The Earth itself. Our planet is constantly moving, orbiting the Sun at a staggering 67,000 miles per hour. That's about 30 kilometers per second. In the time it took me to say that last sentence, you traveled hundreds of miles. We don't feel this because the whole planet is in a state of perpetual free fall around the Sun. No bumps, no braking, just a constant, smooth ride. So, we're on a spinning ball that's hurtling around a star. Surely the Sun is our anchor? Not a chance. Let's kick it away. The Sun is just one of hundreds of billions of stars in the Milky Way galaxy, and our entire solar system is orbiting the supermassive black hole at the galactic center. This orbital speed is almost impossible to wrap your head around. About 515,000 miles per hour, or 230 kilometers per second. Even at that pace, it takes our solar system 230 to 250 million years to make one galactic year. The last time we were in this part of the galaxy, the very first dinosaurs were just starting to show up. This is where the vertigo really hits. We're on a spinning planet, orbiting a star, which is orbiting a galaxy. Is the galaxy, then, the final stop? The great island of matter we can finally call home? Not at all. The Milky Way itself is on a collision course with our nearest large neighbor, the Andromeda Galaxy. Both are being pulled toward each other by gravity, closing the 2.5 million light-year gap at about 250,000 miles per hour. And even this entire cluster of galaxies, which we call the local group, isn't at rest. The whole group is being dragged through intergalactic space toward a massive gravitational anomaly known as the Great Attractor. Our local group is moving toward this region at a truly mind-bending 1.3 million miles per hour, or 600 kilometers per second. Let's just pause and take that in. You're spinning at 1,000 mph. You're orbiting at 67,000 mph. You're revolving at 515,000 mph. And you're being pulled across the universe at 1.3 million miles per hour. All these motions are pointing in different directions, adding up to one complex, spiraling path through the cosmos. That feeling of stillness you have is just the sum of all these colossal, constant speeds. So, we've stripped away the ground, the Earth, the Sun, the galaxy, and even our local cluster. Is there, finally, one ultimate, motionless stage for this cosmic drama? To answer that, we have to look at the fabric of space and time itself. And what we find there isn't an anchor, but the very opposite. A universe defined by inescapable expansion. The big reveal, an expanding universe with no center. For centuries, the model of the universe was basically an explosion. A big bang happened at a point in space, and everything flew out from there like shrapnel. In that picture, there is a center to the universe, the spot where it all began. It's an intuitive idea. And it's completely wrong. The Big Bang wasn't an explosion in space. It was the expansion of space itself. This is the single most important and mind-bending concept to grasp. Let's use the famous balloon analogy, because it's the best one we've got. Imagine the universe is just the 2D surface of a balloon. Now, draw a bunch of dots on it. Each dot is a galaxy. Pick one and call it the Milky Way. Now, start blowing up the balloon. From the perspective of your Milky Way dot, every other dot is moving away. The dots closest to you move away slowly. The dots farther away move away much, much faster, because there's more expanding rubber between you and them. This is exactly what the astronomer Edwin Hubble discovered in the 1920s. He saw that light from distant galaxies was redshifted. Its wavelength stretched out, meaning they are moving away from us. And the farther the galaxy, the faster it was receding. This is Hubble's law. Current measurements of this expansion rate are a hot topic in cosmology, creating a puzzle called the Hubble tension, but they generally show that for every 3.26 million light-years a galaxy is from us, it's moving away about 70 kilometers per second faster. But here's the crucial part of the analogy. Your Milky Way dot sees everything rushing away from it. Does that make it the center? No. Pick any other dot on the balloon. From its perspective, it also sees every other dot moving away from it, with the exact same rule. Farther dots move away faster. Every single dot on the balloon can claim to be the center. That's the reality of our universe. Because space itself is stretching, every galaxy sees all other galaxies rushing away. There's no special vantage point, no center, no edge. The Big Bang didn't happen at a single point, it happened everywhere at once. 13.8 billion years ago, the entire universe, all of space, was in an incredibly hot, dense state. The beginning was a moment in asterisk time, not a point in asterisk space. This is why asking, what is the universe expanding into, is misleading. It's not growing inside some bigger void. The universe is all there is, and the distances between things within it are simply growing. It also explains why you aren't getting taller and the Earth isn't expanding away from the Sun. On smaller scales, gravity and other forces are way stronger than the gentle push of cosmic expansion. We're like raisins in a loaf of rising bread dough. The dough carries the raisins apart, but the raisins themselves don't expand. So, that ultimate anchor we were looking for? It can't exist. To look for a stationary point in an expanding universe is like trying to find a dry spot in the middle of an ocean. You are, by definition, at the center of your own observable universe. But an observer at the very edge of what you can see is at the center of their own observable universe. Every point is the center, which is just another way of saying that no point is. This is a pretty wild idea to get your head around. The fact that you are the center of your observable universe, but that this is true for everyone, everywhere, is one of the most profound truths in all of science. If this journey is expanding your view of the cosmos, then take a second to subscribe and hit that notification bell. We explore big questions about reality like this all the time, and your support is the gravity that keeps this channel in orbit. The why? How relativity forged a groundless universe. So we've established the asterisk. What asterisk? The universe is expanding without a center. But to really get the asterisk why, we have to look at the two pillars of modern physics, both from Albert Einstein: special and general relativity. These theories didn't just describe the universe. They rewrote the rulebook for space, time, and motion, and in doing so, they demolished the very idea of a universal anchor. The old view, from Isaac Newton, was comfortable. He imagined absolute space, a fixed, immovable stage for everything, and absolute time that ticked at the same rate for everyone. It was a tidy, sensible universe. And it was about to be shattered. The first crack came in 1905 with special relativity. It was built on two simple but world-changing ideas. First, the laws of physics are the same for anyone moving at a constant velocity. Second, the speed of light in a vacuum is the same for all observers, no matter how they're moving. This is the truly weird one. If you're on a train and throw a ball, the speeds add up. But if you turn on a flashlight, you measure its light moving at speed (see). Someone on the ground also measures it at exactly (see), not (see) plus the train's speed. The consequences are staggering. If the speed of light is absolute, then space and time themselves must be relative. They must stretch and shrink depending on your motion. This gives us time dilation, moving clocks tick slower, and length contraction, moving objects get shorter. Special relativity destroyed the idea of a universal grid or a master clock. The only meaningful question became, how am I moving relative to you? But that only covered constant motion. For gravity, Einstein gave us general relativity in 1915. He reimagined gravity not as a force, but as the curvature of spacetime. As the physicist John Wheeler put it, spacetime tells matter how to move, matter tells spacetime how to curve. Think of a bowling ball on a rubber sheet. It doesn't pull a marble toward it. It curves the sheet, and the marble simply follows a straight line along that curve. This makes the hunt for an anchor even more hopeless. Since matter and energy warp spacetime, there's no single, flat, universal background. And that brings us to the best candidate anyone has ever found for a universal rest frame: the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, filling all of space. It's almost perfectly uniform. Almost. We see that the CMB is slightly hotter, blue shifted, in one direction and slightly cooler, red shifted, in the opposite direction. This is a Doppler shift, caused by our motion relative to this ancient light. It tells us our solar system is moving at about 370 kilometers per second with respect to the CMB. Our whole local group of galaxies is moving even faster, around 620 kilometers per second. So, is this it? The ultimate rest frame? The answer is a subtle but profound no. The CMB is a useful reference, but it isn't an asterisk absolute one. It's a physical thing, a sea of photons that exists within the universe. A distant observer would have their own asterisk CMB rest frame. They'd see a dipole caused by our motion relative to asterisk them. There's still no universally privileged spot, just a local standard of rest. Einstein's theories show us that an anchor was never in the cards. Our cosmic address in a groundless universe. So, where does that leave us? We started on what felt like solid ground and have kicked away every anchor we could find. We're on a spinning planet, in a spiraling galaxy, being pulled across an expanding universe that has no center. We have found no firm ground, no fixed address, no cosmic "you are here" sign. The gut reaction can be a feeling of being lost. But that's the old way of thinking, the kind that needs an anchor to feel safe. The new perspective, offered by modern cosmology, is way more empowering. The absence of an anchor doesn't mean we're lost. It means we're intrinsically part of the whole. We aren't just watching the universe from a fixed seat. We are woven into the fabric of spacetime. Our motion is the state of the universe. The idea that the universe, on the largest scales, looks the same from everywhere means there are no special places. The view from a galaxy billions of light years away is, broadly speaking, just like ours. This is the great illusion revealed. We think we are in the universe, like it's a box. But we are the universe. We are a thinking, questioning piece of the cosmos, made of atoms forged in long-dead stars, moving by the same rules that govern the dance of galaxies. The most amazing part is that we figured this out. From our tiny, racing platform, with nothing but math and the light from distant stars, we've pieced together a picture of reality that defies all our common sense. We've learned that the bedrock of the universe isn't solid ground, but a dynamic, expanding, and relational web. So the next time you look up at the night sky, don't just see distant, twinkling lights. See the evidence of your own unbelievable journey. Feel the spin of the Earth, the long sweep of our orbit, the grand spiral of our galaxy. Embrace the vertigo. Because being groundless doesn't mean you're adrift. It means you're free. It means you are part of the ceaseless, magnificent motion of everything. Physics just broke the idea of rest. Right now, you probably feel like you're perfectly still, at rest. But in the time it took to say that sentence, you, this planet, and everything on it has hurtled over 100 miles through space. For centuries, we've taken the idea of rest for granted. A book on a table, a quiet room, they all seem to define a state of absolute stillness, a fundamental zero point of the universe. But modern physics has completely shattered that illusion. So, if everything is in constant, frantic motion, what does rest even mean? The answer isn't just a fun fact, it's a profound shift in our understanding of reality itself. It's a journey that takes us from the world we see and feel to the very edge of the cosmos and the dawn of time. The intuitive illusion. Our entire lives are built on the idea of stillness. We seek rest when we're tired. We praise the calm of a lake at dawn. Our language is full of metaphors for being grounded, for finding an anchor in a stormy sea. This intuition is powerful because it's baked right into our biology. Our senses are basically change detectors. Our eyes are drawn to movement. Our inner ears, which control our balance, are great at sensing acceleration, speeding up, slowing down, or turning. But when we're moving at a constant speed, they're completely silent. Think about it. When you're on a plane flying at a steady 500 miles per hour, as long as the ride is smooth, you feel exactly the same as you do sitting in your living room. You can pour a drink, walk down the aisle, and toss a ball in the air, and it'll behave just like it would on the ground. Your body and everything in that plane are in a shared state of motion. So, relative to your immediate surroundings, you are at rest. Your brain, being brilliantly efficient, just cancels out the shared speed. It defines your chair and the cabin walls as still, and judges everything else from there. This is the central trick our minds play on us. We create a little local bubble of rest, and decide that's the absolute truth. A sleeping cat is at rest relative to the floor. A mountain is at rest relative to the tectonic plate it sits on. But what happens when we start peeling back the layers of this cozy illusion? That cat on the floor is also on a planet that's spinning on its axis. Depending on your latitude, that spin is carrying you through space at up to about 1,000 miles per hour faster than the speed of sound. It's a constant, silent rush you've never once felt. And it doesn't stop there. The Earth itself is in a perpetual dance, orbiting the Sun at a blistering 67,000 miles per hour. That's about 30 kilometers every single second. We are all passengers on a colossal spacecraft, completing a journey of nearly 600 million miles every year, yet we feel nothing. The serene stillness of a library is an experience happening aboard a planetary bullet train. For most of human history, this was just a neat bit of trivia. Sure, we were moving, but we were moving relative to the Sun. The Sun, everyone assumed, was the fixed point. And beyond the Sun, there had to be some ultimate, absolute backdrop, a cosmic stage for all this motion. It was this idea of an absolute state of rest that physics would first crack and then utterly demolish. The universe, it turns out, couldn't care less about our desire for a fixed anchor. The classical crack. Newton's universe. Isaac Newton was the first to really tackle the physics of this problem. His laws of motion in the 17th century were elegant, powerful, and mostly, they just made sense. At the heart of his work is an idea that goes back to Galileo: the principle of relativity. Imagine you're on a train, but it's a 19th century steam engine chugging along at a steady 10 meters per second. You're inside a carriage with no windows. According to Galileo and Newton, there is no experiment you could do inside that carriage to know if you're moving. If you drop a ball, it falls straight down, not to the back of the train. The laws of physics are the same for anyone moving at a constant velocity. We call these inertial frames of reference. This is where relative motion truly enters physics. Motion isn't an absolute thing. It's a relationship between two objects. When we say a train is moving at 10 meters per second, we mean it's moving at 10 meters per second relative to the ground. To a passenger on the train, their speed relative to the train is 0. It seems simple. If you're walking forward on the train at 2 meters per second and the train is moving at 10 meters per second, your speed relative to the ground is just 10 plus 2, or 12 meters per second. This is classical, Galilean relativity. But this elegant simplicity hid a deep, troubling question that Newton himself saw. If all motion is relative, then relative to what do we measure the true motion of the universe? If you're on a train and see the station platform moving backward, who is really moving? Intuition screams it's you, not the station. But why? Newton's solution was to propose the existence of absolute space. He pictured a fixed, invisible, cosmic grid that was everywhere and never changed. This was the ultimate frame of reference. An object truly at rest would be motionless against this grid. It was a brilliant philosophical patch to save the idea of absolute rest. There was just one tiny problem. You couldn't see it, touch it, or measure it. For 200 years, Newton's absolute space was a ghost, a placeholder for an answer physics hadn't found yet. The Einsteinian revolution, tearing the fabric. By the end of the 19th century, physics was in crisis. Newton's laws of mechanics were perfect for planets and cannonballs. James Clerk Maxwell's laws of electromagnetism were perfect for light. But the two theories violently disagreed about one thing: the speed of light. According to Newton, speeds should just add up. If you're on a rocket going half the speed of light and you shine a flashlight forward, an observer on the ground should see that light moving at 1.5 times the speed of light. It makes perfect sense. And it's completely wrong. In 1887, the famous Michelson-Morley experiment tried to measure the Earth's motion through the ether, a hypothetical substance that was thought to carry light waves and act as Newton's absolute space. But they found nothing. No matter how the Earth moved, the measured speed of light was always the same. It was a baffling result that broke classical physics. Then, in 1905, a young patent clerk named Albert Einstein proposed a radical solution. He said, "Let's just accept this weird result as a fact." He built his theory of special relativity on two simple ideas. First, the laws of physics are the same for all observers moving at a constant velocity. Second, the speed of light in a vacuum, c, is the same for everyone, no matter how fast they're moving. The consequences of that second idea are truly reality-bending. If the speed of light is absolute, then something else has to give. That something is space and time. Einstein realized that if two people are moving relative to each other, they will experience time differently. A moving clock ticks slower than a stationary one, a real effect called time dilation. A moving object also gets shorter in its direction of motion length contraction. But the real killer for our idea of rest is the relativity of simultaneity. Imagine a long, fast train with a light in the exact middle. Just as the train's center passes a person on a platform, the light flashes. For a passenger on the train, The light travels an equal distance to the front and back, so it arrives at both ends at the same time. Simultaneous. But for the person on the platform, things look different. They see the back of the train moving towards the spot where the light flashed, while the front is moving away. Since the speed of light is constant for everyone, the light going to the back has a shorter trip and arrives first. The light going to the front has a longer trip and arrives second. For the platform observer, the events are not simultaneous. So who's right? Einstein's earth-shattering answer was both of them. Simultaneity isn't absolute. It depends on how you're moving. This one idea completely demolishes a universal rest. To be at rest means your position in space isn't changing over time. But if we can't even agree on what, at the same time, means, how can we possibly agree on a universal, unchanging position? There is no master clock for the universe. There is no universal now. Therefore, there can be no universal here. Newton's absolute space doesn't exist. But Einstein wasn't done. Over the next decade, he developed his theory of general relativity. Here, he proposed that space and time are woven together into a single, dynamic, four-dimensional fabric, spacetime. And mass and energy tell spacetime how to curve. What we feel as gravity isn't a force pulling us. It's just the experience of moving along the straightest possible path through curved spacetime. The sun's massive bulk creates a deep dip in spacetime, like a bowling ball on a trampoline. The Earth, trying to go straight, is guided into an orbit by that curve. It thinks it's going in a straight line, but the very geometry of space is warped. In Einstein's universe, the idea of a simple rest became even more impossible. How can you be still when the very stage you're on is constantly being bent and stretched? The cosmic telescope. A universe in flight. While Einstein was rewriting physics, astronomers were puzzling over faint, fuzzy patches of light in the sky they called nebulae. Were they gas clouds in our own Milky Way, or were they massive, distant, island universes? Galaxies just like ours? The answer came from astronomers like Vesto Slipher and, most famously, Edwin Hubble. Slipher discovered that the light from most of these nebulae was stretched to the red end of the spectrum. This redshift was a Doppler effect, showing they were moving away from us at incredible speeds. Then, in the 1920s, Hubble calculated the distance to the Andromeda Nebula and found it was millions of light-years away, far outside our own galaxy. The island universe theory was correct, but his biggest discovery came in 1929. The farther away a galaxy is, the faster it's moving away from us. This is Hubble's law. The universe wasn't static, it was expanding. But this doesn't mean we're at the center of a cosmic explosion. A good analogy is to imagine baking a loaf of raisin bread. As the dough rises, every raisin moves away from every other raisin. A nearby raisin moves away slowly, while a distant one, carried by more expanding dough, moves away much faster. From the perspective of any raisin, it looks like it's the center of the expansion. The dots aren't moving through the dough. The dough itself is expanding, carrying them along. This is the key. Galaxies aren't rocketing through space. Space itself is stretching, creating more distance between them. The discovery of an expanding universe was the ultimate nail in the coffin for absolute rest. If the very fabric of spacetime is stretching, where could a still point possibly be? It's like trying to find a point of rest in the middle of an explosion. There is no fixed backdrop, because the backdrop itself is the thing that's expanding. The grand synthesis, the final nail in the coffin. So, we've seen Einstein show there's no universal now, and Hubble show that the entire cosmic fabric is expanding. Is there anything we can measure our motion against? Some kind of ultimate background? Amazingly, yes. It's called the cosmic microwave background, or CMB. The CMB is the oldest light in the universe, a faint afterglow from the Big Bang itself, just 380,000 years after it began. This radiation fills all of space and is almost perfectly uniform. It's the closest thing we have to a cosmic rest frame. So, are we at rest compared to the CMB? Not even close. Scientists have found a clear pattern in the CMB. It's slightly warmer, blue-shifted, in one direction and slightly cooler, red-shifted, in the opposite direction. This is the signature of our motion. The data shows our solar system is moving at about 370 kilometers per second relative to this ancient light. When you include the motion of the Milky Way, our speed is even higher, around 600 kilometers per second. That's over 1.3 million miles per hour. This is our peculiar velocity, our own local sprint on top of the cosmic expansion. This raises one last, crucial question. If space is expanding, why aren't we expanding? Why isn't your chair or the planet getting bigger? The answer is that cosmic expansion is a very gentle push that only wins out over enormous, intergalactic distances. On smaller scales, gravity is king. The Earth's gravity easily holds you together, the Sun's gravity holds the solar system together, and the Milky Way's gravity holds its stars together. Gravity creates little islands of stability that are protected from the cosmic stretch. And so, we arrive at the grand synthesis. There is no absolute rest. The fabric of space is expanding. And even relative to the oldest light in the universe, we are in frantic motion. Rest is a useful illusion, a fiction we create in our local, gravity-bound bubble. But it has no fundamental reality. The true, default state of the universe is not stillness. It is motion relentless, universal, and inescapable. For thousands of years, we looked to the stars for a sense of permanence. We saw them as fixed points in an orderly, static universe. But the story physics tells us today is far more dynamic and, honestly, way more interesting. We started with the simple feeling of being still and saw how physics dismantled that idea piece by piece. Einstein tore up the old rules of space and time, and Hubble showed us the entire cosmic stage is expanding. The idea of rest is a local illusion. It's a story we tell ourselves inside our own little bubble, a temporary truce in a universe defined by motion. From the quantum jitter of particles to the recession of distant galaxies, the universe is, and has always been, a part of the dance. So the next time you feel perfectly still, take a moment to appreciate the illusion. Remember you're a passenger on a tiny spacecraft called Earth, spinning, orbiting the Sun, which is itself speeding through our galaxy as the entire galaxy is carried on the expanding currents of spacetime. The universe isn't a static stage, it's a grand, unfolding performance. And you're not just a spectator, you are part of the dance. Why you aren't actually motionless in an expanding universe? Right now, you think you're sitting still. But you're on a planet that's spinning at about 1,000 miles per hour. That planet is orbiting our Sun at a blistering 67,000 miles per hour. Our entire solar system is being dragged around the center of the Milky Way at over 500,000 miles per hour. And the Milky Way itself, along with our whole cosmic neighborhood, is being pulled through intergalactic space at over 1 million miles per hour toward a mysterious spot in the sky we call the Great Attractor. And yet, you are perfectly motionless. You don't feel a thing. You can take a sip of coffee without it flying off into the cosmos. This isn't a riddle. It's a fundamental clue about the nature of our reality, and it points to a truth about the universe that is far stranger than you might imagine. The secret isn't about how fast we are moving through space, but how space itself is carrying us on an incredible, silent journey. To figure this out, we have to become cosmic detectives. We'll follow a trail of clues that starts with a faint stretching of light from distant galaxies and ends with the very fabric of reality expanding all around us. This is the story of what that expansion truly means for our sense of place and motion in the vastness of the cosmos. The first clue: a universe in flight. Our investigation starts about a century ago, in a world that imagined a totally different universe. For most of human history, even for giants like Isaac Newton and Albert Einstein, the universe was assumed to be a static, eternal, and unchanging stage. The stars were distant suns, sure, but the grand cosmic theater itself was thought to be motionless. The prevailing wisdom, even into the early 20th century, was that our own Milky Way galaxy was the entire universe. It was a comfortable, manageable, and completely wrong picture of reality. The first hint that this tidy, static universe was about to be shattered came not with a bang, but with a whisper of displaced light. In the 1910s, an astronomer named Vesto Slipher was at the Lowell Observatory in Arizona, painstakingly analyzing light from what were then called spiral nebulae. These were faint, swirling clouds of light, and astronomers fiercely debated what they were. Gas clouds in our own galaxy? Or were they unimaginably distant, island universes, entire galaxies in their own right? Slipher used a technique called spectroscopy, which spreads light into a rainbow of its component colors. Imprinted on these cosmic rainbows are dark lines that act like chemical fingerprints. Slipher noticed something strange. For nearly all the spiral nebulae he observed, these fingerprints weren't where they should be. They were shifted toward the red end of the spectrum. This effect, called redshift, wasn't a total mystery. It's the cosmic version of the Doppler effect, the reason an ambulance siren sounds higher as it approaches and lower as it drives away. When a light source moves away from you, its light waves get stretched out, shifting them toward the red part of the spectrum. A blue shift, on the other hand, would mean it's moving toward you. What Slipher found was that almost every single one of these distant nebulae was rushing away from us, some at incredible speeds. It was a profound and unsettling discovery, the first piece of evidence that the universe wasn't static at all. But without knowing how far away these objects were, the full picture remained a mystery. The clue was on the table, but the detective who would crack the case was just getting started. Enter Edwin Hubble. Working in the 1920s with the world's most powerful telescope at the time, the 100-inch Hooker telescope on Mount Wilson, Hubble's first mission was to settle the nebula debate. He did this by finding a special type of star inside the Andromeda Nebula, called a Cepheid variable. These stars are a gift to astronomers because they pulsate, and the timing of their pulse is directly tied to their true brightness. They're standard candles. If you know how bright something truly is, you can figure out its distance by measuring how dim it appears. It's like seeing a distant headlight. The dimmer it seems, the farther away you know it is. When Hubble measured the Cepheids in Andromeda, he calculated their distance. The number he came up with was staggering. Nearly 1 million light-years, placing Andromeda far outside the Milky Way. It wasn't a gas cloud, it was another galaxy. In that moment, the known universe got a whole lot bigger. But Hubble didn't stop. He now had the key Slipher was missing: a way to measure both the speeds and the distances of these new galaxies. Throughout the 1920s, Hubble and his assistant, Milton Humason, measured the distances and redshifts for dozens of galaxies. When they plotted their results, a stunningly clear pattern emerged. With few exceptions, every galaxy was moving away from us. And not just that, the farther away a galaxy was, the faster it was receding. A galaxy twice as far away was moving twice as fast. This simple relationship became known as Hubble's law, and it was the first real proof of an expanding universe. But this discovery created a deeply uncomfortable paradox. If everything is moving away from us, doesn't that make us special? It sounds like we're at the very center of a cosmic explosion. This was the obvious, but profoundly wrong, conclusion. It would have tossed us back to a pre-Copernican mindset, putting humanity at the center of creation. The evidence pointed to a universe in motion, but the interpretation seemed to lead to an absurd conclusion. The mystery had deepened, and solving it would require a whole new way of thinking about space itself. Cracking the case. The fabric of spacetime. The idea that we're at the center of the universe is tempting, but it goes against a core scientific idea. The principle of mediocrity. It's the notion that we don't hold a special, privileged place in the cosmos. To solve the puzzle from Hubble's data, we needed a model where every observer, in any galaxy, would see the exact same thing. All other galaxies rushing away from them. How could everyone be at the center at the same time? The answer is as elegant as it is mind-bending. The galaxies aren't flying through space. Instead, the space between the galaxies is expanding, carrying them along for the ride. The classic analogy is to picture a loaf of raisin bread dough rising in an oven. Imagine you're standing on one of the raisins. As the dough expands, what do you see? Every other raisin moves away from you. A raisin that was an inch away is now 2 inches away. A raisin that was 2 inches away is now 4 inches away. The more distant raisin appears to move faster. This perfectly matches Hubble's law. Now for the crucial part. If you hopped over to any other raisin, you'd see the exact same thing. From any point in the dough, it looks like you're the center of the action. There is no center inside the dough. The expansion is happening everywhere at once. The raisins themselves aren't moving through the dough. They're being carried along by the expanding dough itself. This collective motion is what cosmologists call the Hubble flow. Another way to think about it is to imagine drawing dots on a balloon. Each dot is a galaxy. As you blow up the balloon, the rubber surface stretches, and every dot moves away from every other dot. Pick any dot, and you'll see all the others receding. Again, there is no center of the expansion asterisk on the surface of the balloon. The center is inside the balloon, in a third dimension the 2D universe on the surface can't access. This helps us see why asking, what is the universe expanding into, might be the wrong question. The expansion is a property of our three-dimensional space itself. It doesn't necessarily need an outside to expand into. This brings us to the aha moment. The redshift that Slipher and Hubble saw isn't mostly a traditional Doppler shift from galaxies speeding through static space. It's a cosmological redshift. As a photon of light travels for billions of years from a distant galaxy to our telescopes, the space it's traveling through is continuously expanding. This expansion literally stretches the light wave, increasing its wavelength and shifting it toward the red. The longer the journey, the more the light gets stretched. This is why more distant objects have higher redshifts. It's a direct measure of how much the universe has expanded since that light began its trip. So, the great clue of the receding galaxies wasn't pointing to a special center. It was pointing to a dynamic, evolving reality where the stage itself is growing, carrying everything with it. And we are simply passengers on this grand, silent current, the Hubble flow. The revelation. Motionless on a cosmic river. So now we can finally solve the paradox we started with. How can you be hurtling through space at millions of miles per hour and still feel perfectly still? The answer is in the difference between two kinds of motion. The Hubble flow and what astronomers call peculiar velocity. The Hubble flow is the overall expansion of space, carrying galaxies along like those raisins in the dough. A galaxy that is moving only because of the expansion is said to be comoving. It's at rest with respect to the stretching fabric of spacetime. Peculiar velocity, on the other hand, is any motion a galaxy has in addition to the Hubble flow. It's a galaxy's own, local motion through space, and it's caused by the one force that can fight back against the expansion: gravity. While the universe is expanding on the largest of scales, on smaller scales, it's lumpy. Gravity from galaxies and clusters of galaxies pulls on their neighbors, creating these peculiar, or individual, motions. Think of the Hubble flow as a vast, deep river. Every boat on it is being carried downstream by the current. But some boats have little motors, pulling them side to side or even slightly upstream relative to the water around them. That extra, local motion is the peculiar velocity. For a very distant boat, its tiny motor speed is nothing compared to the powerful flow of the river. When we look at a galaxy billions of light years away, its peculiar velocity is completely swamped by the massive recession speed from the Hubble flow. But for nearby boats, it's a different story. This is exactly what we see in our own cosmic neighborhood. Our Milky Way is part of the local group, a collection of more than 50 galaxies. Within this group, gravity is king. The expansion of space is still happening here, but the gravitational pull between the galaxies is so strong that it completely overpowers it. The local group isn't expanding. It's gravitationally bound together. The best example is the Andromeda galaxy. Based on the Hubble flow, Andromeda should be moving away from us. But it isn't. Its light is blue shifted. Andromeda is hurtling toward us at about 250,000 miles per hour, 110 kilometers per second. That's its peculiar velocity, driven by the mutual gravity between our two galaxies. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge. This local gravitational drama completely overwhelms the gentle current of cosmic expansion. So, let's connect this back to you. You feel motionless because you aren't accelerating. You're motionless relative to the Earth. The Earth is motionless relative to the Sun. And our entire solar system is part of a huge, gravitationally bound island called the Milky Way. The atoms in your body aren't flying apart because the forces holding them together are astronomically stronger than cosmic expansion on that tiny scale. The solar system isn't expanding. Our galaxy isn't expanding. You feel still because you are on one of these stable, gravitationally bound islands, moving along with your entire local environment. But that entire island, our whole local group, is being carried along on the river of expanding spacetime. Your feeling of stillness is an illusion, but it's a very localized one. You are, in the most literal sense, just going with the flow. The grand motion of the universe isn't something you feel, because it's happening to everything. It is the new, cosmic definition of standing still. We've just peeled back a layer of reality to see the deep truth behind our place in the cosmos. If your mind is spinning with these ideas, then you're in the right place. Consider subscribing to keep exploring the biggest questions about our universe. By joining us, you become part of a community of cosmic detectives, all trying to piece together the grand puzzle of reality. The wider implications. A new cosmic perspective. Understanding the Hubble flow doesn't just solve a paradox. It revolutionizes our entire idea of the universe, forcing us to embrace a much grander, and frankly stranger, reality. First, it absolutely removes us from the center of the universe. The raisin bread and balloon analogies show that in an expanding space, every point appears to be the center. There is no special spot. This is formalized in the cosmological principle, which states that on the largest scales, the universe is basically the same everywhere and in every direction. An expanding universe like this has no center and no edge. Second, the expansion creates a fundamental limit to what we can ever see. Because light travels at a finite speed, looking out into space means looking back in time. We see Andromeda as it was 5 million years ago. This makes our telescopes time machines, but it also creates a horizon. There are galaxies so far away that their light, traveling since the beginning of time 8 billion years ago, still hasn't reached us. Worse, because the expansion is accelerating, there are galaxies whose light will never reach us. The space between us is expanding faster than light can travel through it. This doesn't violate Einstein's theory. Nothing can move through space faster than light, but the space itself is being created so rapidly that light can never finish the journey. Our observable universe is just one bubble in a possibly infinite cosmos we can never fully access. Third, the expansion is the foundation of the Big Bang theory. If the universe is expanding today, it must have been smaller, denser, and hotter in the past. Run the clock backward, and everything in our observable universe converges onto a single point of unimaginable heat and density about 13.8 billion years ago. The Big Bang wasn't an explosion in space. It was the beginning of the expansion of space, everywhere at once. Maybe the most startling discovery came in 1998. For decades, astronomers debated whether gravity would eventually slow the expansion and cause a big crunch, or if the expansion would win, leading to a big freeze. Two teams set out to measure how much the expansion was slowing down. They found it wasn't slowing down at all. It was accelerating. For the first several billion years, gravity did put up a good fight, but about 5 to 6 billion years ago, a mysterious influence called dark energy started to take over, pushing space-time apart faster and faster. We still have no idea what it is. It seems to be a property of empty space itself. Today, dark energy is thought to make up nearly 70% of the universe. Ordinary matter, the stuff of stars, planets, and us, accounts for a mere 5%. We're just foam on a deep, dark ocean. This paints a strange picture of the future. As acceleration continues, all galaxies outside our local group will eventually cross that cosmic horizon and vanish from our view. Future astronomers on our lonely island universe would have no evidence of other galaxies, no Hubble's law, and no way of knowing the universe was ever expanding. They would, ironically, return to the wrong picture of the universe we held in the early 20th century. And the story isn't over. A persistent mystery known as the Hubble tension plagues cosmology today. When we measure the expansion rate using nearby objects, we get one number, about 73 kilometers per second, (mpc). But when we use light from the Big Bang to predict the rate, we get a different one, about 67 kilometers per second, (mpc). These two methods stubbornly refuse to agree, suggesting there's still a missing piece in our cosmic puzzle. The stillness of the journey. We started with a simple feeling, being still. Yet, by following the clues, the faint red glow of distant galaxies, the pulse of dying stars, the afterglow of the Big Bang, we've unraveled that feeling into a profound cosmic truth. Our sense of stillness is a local illusion. We're at rest on a gravitationally bound island called the Milky Way. But this island, and every other island in the cosmos, is a passenger on the most majestic journey imaginable. We are being carried by the very fabric of reality as it stretches and grows, a process that began 13.8 billion years ago and is, against all odds, speeding up. You aren't moving through the universe so much as you are moving with it. Your personal state of rest is tied to the cosmic state of rest, the silent, invisible, all-encompassing Hubble flow. The next time you look up at the night sky, remember what you're truly seeing. You're not a static observer watching a static scene. You are a traveler, looking out from the deck of your galactic ship. The lights you see are the receding taillights of other travelers, each carried away on the same unseen current. The stillness you feel is not an absence of motion, but the quiet hum of taking part in the expansion of everything.